I'll be describing that very soon. So I'd like you to consider the alum cycle, which was developed. It was studied and designed, and a design for the 300 megawatt plant was prepared by our students, and their paper appeared in Chemical Engineering Progress in December of 2021. It was entitled Carbon Capture by the Alum Cycle. Okay, now I'd like to spend a little time just taking you through this. I can't describe every detail. I just don't have the time to do that. You can certainly read about it in this particular paper and in the report that it refers to. Okay, well, let's begin here with natural gas. And the natural gas is going to be compressed up to about 300 bar. Okay, okay, it is sent to a combustor. And two other streams are sent as well. I'll tell you more about them very shortly. Both of them are highly concentrated in carbon dioxide. One of them has oxygen, okay, that is just enough oxygen to burn the natural gas. Okay, so the combustor essentially burns the natural gas, and its effluent, this stream that leaves, is at 1,130 degrees centigrade, and it's 93 mole percent carbon dioxide and 7 mole percent water. Okay, all right, it goes to the turbine, and in the turbine it is reduced in pressure to 30 bar, okay, as it generates power, electrical power. Okay, the temperature is 772 degrees centigrade. Okay, now this is going to be cooled, and I'll explain to you the cooling in what is known as a recuperator. And the recuperator is going to cool it down to a temperature of about 27 degrees centigrade. Okay, and in addition to being cooled with cooling water, it's going to be expanded to 17 bar. Okay, and the water then will be, there'll be a vessel here, a vapor liquid separator, we call it a flash vessel, and the liquid water will be taken off, and the carbon dioxide will be sent in the vapor stream. This will be compressed, and it's compressed to about 120 bar. Okay, it takes about 142 megawatts of power. Okay, that's about half as much as going to be generated here. So clearly this turbine has to then produce 300 megawatt plus that 142 megawatts. Okay, now the output from the compressor, okay, is now at 120 bar, and that is sent for sequestration, okay, underground, in an underground cavity. And it is very pure. It's almost 100%, 99% pure. Okay, now some of this is returned, okay, and it is liquid-like now. Okay, it's pressed, and so it gets pumped, not pressed, okay, and is sent to the recuperator where it gets heated up. And it then gets sent to the combustor. It is nearly pure CO2. Okay, now in the meantime, some of it is sent over here, and it is mixed with oxygen from the air separation unit. Just enough oxygen to react with the natural gas. Okay, that then gets pumped, okay, through the recuperator, heated up, and is sent to the combustor. So, okay, the natural gas comes into the combustor, it then sees the oxygen, and it then is burned. And we then use the turbine and generate power. Okay, so that's the way it works. Okay, keep in mind, this is a separation unit. it is cryogenically operated, and it requires a great deal of compression power, okay, to generate the oxygen that's needed. Keep that in mind. Okay, so that's additional power that would have to be generated by the turbine. Move on. Okay, go back now to the 50 megawatt net power demonstration plant in La Porte, Texas, which is in Houston, Texas, okay, an energy center. And I'm going to try to describe this to you quickly, okay? Here comes the natural gas right here in this green stream, okay? And it's going to get compressed, as I explained to you, okay? And it gets compressed up and it goes to the combustor and then to the turbine, okay? Now I'll tell you more about how the CO2 comes back into the combustor, but let us look now what happens. Coming out of the turbine is a stream that is nearly, it's got a lot of, about 93% CO2 and 7% water. Okay, we send it to a heat exchanger, okay? This is called a recuperator, and it is then cooled down, and it's further then expanded and sent to the water separator. The water is removed. Now the CO2 is sent back to the main CO2 compressor that I told you about. Okay, and then we have a sequestration going underground. In the meantime, from the air separation unit, we get oxygen, and it gets combined with CO2 from here, and you can't see it, but it's sent back to the combustor. It goes through this heat exchanger and gets heated up first. Okay, similarly, CO2 then comes and gets pumped up in as well into the combustor. Okay, that's how it runs. This is a 50 megawatt plant in La Porte, Texas. Okay, now, in about the year 2021, 22, okay, Net Power announced that it is producing in Odessa, Texas, which is Weston, Texas, all right? They are producing, preparing a 300 megawatt power plant, and that's supposed to come online in 2026, so keep that in mind. Okay, now moving on. The other process that the students considered is the natural gas combined cycles. Okay, this is essentially a Brayton cycle and a Rankine cycle, a steam cycle. Okay, it's combined. And after that, after this, they then take the CO2 and remove it and then compress it. Okay, so you can see how it works here. Okay, natural gas comes in with air, okay, it gets compressed, okay, goes to the combustor, gets burned, goes to the gas turbine, okay, power is generated, all right, 300 megawatts of power, okay, all right, now, in addition, well, not quite 300 from the gas turbine, but you'll see. The effluent from the gas turbine is very hot, so it then goes and it heats now, okay, a liquid water, okay, it heats essentially to generate steam. And the steam, this is at elevated pressure. The steam then runs the turbine. Okay, so the combination of this steam and this and what comes in the end and the power from this is going to be 300 megawatt. Okay, now then coming out of the steam turbine, we have a condenser, then we go to a pump, we build the pressure again. Okay, you get the idea. Okay, meanwhile, the flue gas comes down here. Okay, it's got the CO2 in it. All right, now we're using a amine scrubbing unit, and the amine scrubbing unit then essentially recovers, okay, the CO2 and sends it. It has to compress it now because it's at low pressure, and it has to compress it and send it off for sequestration. Okay, that's how this process operates. Right now, let's just talk quickly. I don't know about my timing. I think it's okay. I hope so. Okay. Now, the students the design group, did simulations with profitability analyses, okay? And they began by simulating the processes using Aspen Plus, the major process simulator. They estimated the equipment sizes and the installation costs. We call that CapEx, the capital expenses, okay? All right, they estimated the operating costs. We call that OpEx, the operating expenses. They calculated the net present value, okay, NPV, okay, at 15% cost of capital over 20 years of operation, okay? Now, you need to know this. In the United States, okay, Congress then passed a bill to provide carbon tax credits. It's the 45Q tax credits, they're called. And these were required to break even, okay? So now what you need to keep in mind is that in 2017, okay, you got a $22.66 for every million, okay, or I'm sorry, $22.66 per million ton of CO2 sequestered, okay? Now, that has been projected to increase to $50 per million ton by 2026, okay? Keep this in mind. Now, the design group estimated the net present value for each process as a function of the 45Q tax credit in dollars per million ton of CO2 sequestered. Now look at this. If the tax credit was at $50 per million tons, well, then the natural gas combined cycle with carbon dioxide removal, CDR, lost less money than the alum cycle. But then as the tax credit increased in value, and it has not been projected to do that, but if it did, at this point, the alum cycle would lose less. But you see, when you get up to a tax credit of $155, the alum cycle now, okay, has a zero net present value, which means it has a 15% investor's rate of return to break even, basically. All right? So the alum cycle becomes more favorable than the natural gas combined cycle with the carbon dioxide removal. That's important to recognize. Okay, now I need to continue. I'm almost done. I hope the timing is right. Okay, we are doing our research. Okay, and these are the alternatives. The first is to increase the thermodynamic efficiency by achieving improved heat integration. Those of you that know about heat integration, what you do is you reduce the delta T minimum, okay? And that would be done in the recuperator and other heat exchangers. That's one possibility. Another is to adjust the carbon dioxide temperature and pressure to be able to pump liquids rather than compress vapors. It's so much more expensive to purchase compressors and install them and to operate them. Okay, a third would be to avoid the cryogenic distillation when recovering oxygen from air. Okay, the compression for refrigeration is very expensive. Okay, we would consider electrolysis of water using renewable energy, solar, wind, geothermal type energy. More and more that's being considered now. And when you would do that, you would get the oxygen you need for combustion in the alum cycle, and you would react the hydrogen that you get from electrolysis. You would do that with CO2, and you would obtain high-value hydrocarbons. Okay? These are the research alternatives we're looking at now. And I want to conclude now, in the time I have, hopefully this will go very quickly. The utilization of natural gas for power generation with CO2 sequestration is promising, especially using the alum cycle with water electrolysis and not an air separation unit that operates, okay, cryogenically. And this would provide the oxygen for combustion and also hydrogen that would react with CO2, and it would yield high-value hydrocarbon products that reduce the need for CO2 tax credits. We think this looks very, very favorable. I hope you found this to be helpful to you. I was hoping that this would be live so that I could answer questions, but unfortunately it doesn't appear that was the case. If there are any questions, I'll be happy to try to answer them now.
Thank you for that. Is there any questions to? Okay, so we'll be collecting the questions and then we will be reading them out to you. Okay. Sorry for that.
Thanks. It was a wonderful talk, a very timely one. I hope you can hear me all right. And I'm sitting in the auditorium 10,000 miles away from you. And I have a very simple question.
Okay.
That your process and many others, the sequestration of CO2 to a great extent means underground geological storage, okay?
Yes.
No matter how much methane or how much other things we do, so that has to go underground and through geological storage. Now, there are many places, many countries, Japan being one of them, because this is earthquake prone, there's hardly any geological storage, deep sea is expensive.
Okay, I'm not understanding much of what you're saying. You're talking about something to do with storing the CO2 underground, but I'm not understanding, the words are not coming through sufficiently well right now.
Okay, so
other than that.
You got it right. You know, I want to know that this geological storage, does it in the long run pose a problem for the upstream of the process? That means lack of availability or the transport cost or the compression which is needed. Does the geological storage will turn out to be a major obstacle for sequestering CO2 in the future? That's my question.
Well, I didn't understand much of what you were saying. I think you're concerned about these underground cavities and their ability to hold the CO2 properly under pressure. That would certainly be a concern, but my understanding is that the cavities can be located in such a way that it is not a problem. Another thing to keep in mind that I'm mentioning is that if we proceed to produce hydrogen using electrolysis, then we can react it with CO2. And much of the CO2 can then be put into high-value hydrocarbons, which can be sold. And you would have less to put underground. That would be a big advantage. That's the best I can do to answer the question. I think you probably asked a question that I don't fully understand.
Thank you very much. Is there any other questions to Professor Seder? I guess. Okay. Thank you very much, Jessica and everyone here. So, can you move forward to the next one?
Hello. Thank you, Professor Sitter, for your wonderful talk. Uh,
Okay, thank you. I'm happy to have done it.
yes, thank you so much for being there so late and delivered this lecture. I'm sure you must be feeling sleepy at at this point of time, but thank you so much for this.
Okay, all right. Enjoy the rest of the morning. I'm going to sleep.
Yes, sure, sir. Thank you so much for being there.
Okay, take care now.
So, moving on to our next plenary speaker. So,
Recording stopped.
it's my great pleasure to introduce Professor Orp Sen Gupta. So, okay. So, for well over 3 decades, Professor Orp Sen Gupta's research has encompassed nearly every aspect of water science and technology, from drinking water treatment to desalination to municipal wastewater reuse to resource recovery. Dr. Sengupta is internationally recognized for advancing and expanding the field of ion exchange science and technology and applying it for development of sustainable technologies and new materials. He is the inventor of the first reusable arsenic selective hybrid anion exchanger nanomaterial, HYDES Nano. Over 2 million people around the globe currently drink arsenic safe water through use of HYDES Nano. For his research and scholarly contributions, Professor Sengupta received many national and international awards, including 2004 International Ion Exchange Award at the University of Cambridge, England, 2007 Granger Challenge Silver Award from the National Academy of Engineering, 2009 Lawrence K. Cecile Environmental Award from the American Institute of Chemical Engineers, and 2012 Intel Environmental Award for Technology Benefiting Humanity, to name a few. Dr. Sengupta is a fellow of AICHE, ASCE, and NAI National Academy of Inventors. Dr. Sengupta, the floor is all yours.
Okay. any event, we're a little late. I'll go ahead, and I believe I'll be able to keep my talk contained in half an hour or 35 minutes. The title of the lecture is fairly self-explanatory. And this is centenary, and I got my undergraduate degree from this department just about 50 years ago. So I am a half centenary person. And in the process, we always look back at what we learned from here, and some of them kind of stand out depending on the nature of the people, and kind of provides a different kind of perspective to the profession, to the technology world, and also to the world we live in. So let me start with something very simple, yet kind of problematic in terms of the philosophy of life in this planet. What we back at what we learned from here, and some of the kind of stand out depending on the nature of the people, and kind of provides a different kind of perspective to the profession, to the technology world, and also to the world we live in. That's very simple, but yet kind of problematic in terms of the philosophy of life. What process goes back at what we learned from here, and some of the kind of stand out depending on the
Okay, are we back again? I guess the microphone is working now. Is the microphone working now?
Hello, I guess the microphone is back. So let me start, and this is life, that's engineering. Engineering without problem is no engineering. Okay, so this is an example of engineering.
Direct
And
audio
we have to
direct.
overcome that. So let me continue as long as my talk is comprehensible to you. So this is something I was kind of going to mention about my early education in chemical engineering. So this is, you all know, this is high temperature, this is low temperature, and always heat flows from high temperature to lower temperature. This is the basic second law of thermodynamics. If you replace that by high voltage to low voltage, then the current flows from high voltage to low voltage. In the same way, our theory is high concentration to low concentration. The solvent always flows from a region of higher concentration to a region of lower concentration. We call that diffusion. So this is the kind of heart and soul of, in many ways, every field of chemical engineering. But then when I look at what has been going on in our planet for quite a long time, it continues. Here I would replace high concentration, prosperous, means more wealth, more money, and then impoverished, means We are engineers, we have to make good changes. It is good to keep that in mind. With that thing, and I'll come back probably in the last 1 or 2 minutes during my talk, because after all, we try to make good changes in the world. When I became a full professor in the United States, there is a way of getting there. Then I kind of took it to my heart that I'll try to take 1 or 2 problems, which probably are not funded. Maybe there are more difficulties, but if I can kind of take a crack at them, then the chances the good things will happen. Maybe it will not happen because this is a very challenging thing, but it is always nice to have kind of good find, in your system. And it has many small things I did, other things I did. The 2 things which I would like to talk about, which basically fill up this backwater. One is the area of access to self-drinking water. Okay? After all, I'm from India, I've traveled to many, many countries. This is something close to my heart. This has been going on for more than 25 years. This is relatively new for about 3 years. The previous speaker, he's from one side, and I'll tell you about what I have been doing or started doing. So that's the 2 things, but they're also very broad in perspective. They're more than research, they're sort of larger than life. This is a photo, and you can see here, it was taken in 1995, which is more than 25 years ago. That's how it started. This is not far away from here. This village is in north of 24 Parganas, a place called Shuknaur or Halka. There's plenty of water. There's no shortage of water. But the surface water is not contaminated with typhoid or other terms. That's why naturally filtered groundwater is the resource. United Nations through UNICEF sank maybe millions of such hand-operated wells in India, Bangladesh, Cambodia, Vietnam, many other places. Okay, for good reasons, because this is filtered water. And this is the one in Bangladesh, and you can see water everywhere. But this poor lady in this earthen vessel is collecting water from underground. The same reason. It is not for lack of access, it is that safety nature of the groundwater as opposed to the surface water. But then something happened which people didn't foresee. Mother Nature was not so motherly. So there was a very tiny concentration of arsenic in groundwater. People didn't know. Arsenic doesn't have any color, it doesn't have any odor, it doesn't have any taste. So people didn't know about it, they drank it. And these are the pictures of people which I took the photograph kind of myself and the people who work with me. And there are many more gruesome pictures. That's not the point. The point is that millions of people were affected. These are manifestation of arsenic poison and very low concentration. We were not aware of it. And then when we became aware of it, then this is a well in Cambodia, near the capital of Phnom Penh, on the bank of Mekong. Government just paid suggesting don't drink water from there. But they have to have a separate source. So that became the challenge. At that point, kind of long ago, I got involved. As I said, also I started learning. Then a few things happened. So this is in North Jewish Parganas, very close to Bangladesh border. What we did initially, we didn't change the culture of the place. Still, the thing well. This little girl is coming in the real time. She's using this hand pump and getting the idea was good for once through. That means use it for once, then you throw it away. There's no way of using it. So after it has been used, they were left behind, stood around in villages which doesn't have any kind of land disposal or hazardous waste disposal facility. So this is itself is a crisis. And from there, kind of got a research idea. These materials were very fragile, you can see that. That's why they were used for upcycle. The idea came, just like the C problem come up with the idea. The idea came is that these are the nanoparticles of iron oxide. This is a surface-dependent substrate. If we can somehow put this nanoparticle inside the polymer, then the chance is then we'll have a material which have hydraulic permeability like this polymer will, but the capacity for arsenic removal would come from the nanoparticles. In the beginning, we thought it would be an easy task, but you know, this is why it is research. So it was in 96, 97. It took us nearly 6 hours, 6 years to come to the solution. Obviously, the fundamentals come from this guy, Frederick Donnan, and his principle known as Donnan exclusion and Donnan membrane principle. This goes back 100 years ago. We took advantage of that because in the beginning it was extremely difficult to make such particles. And then finally, we got these people Iceis nano hybrid anion exchange resin. That means it's an anion exchanger within which we were able, after 6 years of effort, to put iron oxide nanoparticles. And this was a Eureka moment. This is the nanoparticle TEM picture. So we made 2 grams of material in 2003. And 2023, 20 years, maybe 200 million grams of this material have been commercially manufactured and are in use at least in half a dozen countries around the world, including USA and India. This is a plant in USA. There are many others. It has a lot of bells and whistles, but it uses this material, HRX nano, hybrid reduction nano. But the key point is though, that's not the first one. The first HIX nano was tried, validated, confirmed in a village in North Jewish Performance, which is not too far from here, which means the crisis at home can create new knowledge, new science, new technology, which can even travel from the east to the west. And this plant in the east, it has changed now. It's much bigger, much more developed in many ways. This is in Bangladesh, the same kind of, this is in Cambodia, which basically can reduce arsenic to a very, very low level. This is a village where a lot of people died of cancer. And this little girl, you can see, iron is also there. This is how it looks, raw, and this is how it looks treated, and also arsenic is there. This is not just for the community. This is a kind of scaled up big plant. This is 92. Nearby, there is one of 150 meter cube per hour plant by the government finance, and we did the engineering. So this is, to my knowledge, that's now the largest arsenic removal plant in the world, okay, based on the technology which was developed. About 3 million people, difficult domestic, larger plant community, they run them. This is, you can probably read this, it's the HIX2 Nano 200. This is a company called Water Innovation through Science and Technology. It was founded in my lab, and it is being manufactured as I speak in the outskirts of Kolkata, India, you know, and that's the story about science and technology. For So that's also an issue there. So CO2 is hurting us. You got your Amphan, maybe next year will do something. Iceis is being hit by one thing and another. So that's an ongoing thing. And CO2 is the culprit. So there are three ways of tackling this thing. The earlier one, there was a lecture there, you heard it. One is replacing fossil fuels with renewable energy sources. What is said, Dr. Cedar, it partly embraces that, because they are really kind of doing away with coal, taking natural gas and generating hydrogen. So that's one aspect. The other one is controlling CO2 emissions into the atmosphere. Wherever it is coming, flue gas stack, there is that. You go there, capture the CO2. That's all. And there is another third avenue, which is known as direct air capture of CO2, which means you go to any place, anywhere in the world. Like in this room, there's a tiny amount of CO2 is there in the atmosphere, about 400 ppm. Can we capture that CO2? If we keep capturing CO2 all over the places, that's also a way of doing it. But it's very challenging. The challenge comes from the fact the CO2 concentration is very, very low. So thermodynamically we understand that CO2 removal, separation point of view, would be a very, very challenging problem. So this is my area of research, which is growing, and this is also a kind of a global crisis. So that's the incentive. Whether I fail or lose, that's a great thing. This is the thing I said, that carbon dioxide only 400 ppm or 0.04%. All other things are small. But this is slightly acidic gas. Okay, that's the difference we'd like to capture. Very quickly, I'd like to show how direct air capture works. Very simple thing, Just you take air from any place, use a fan, pass it through some kind of a filter which can capture CO2, then you get the CO2-free air goes out, then whatever comes at the end is becomes exhausted, then you heat it up, CO2 gets released. Very much like the way the last speaker was talking about. Then you collect that CO2 and then you concentrate, put it geologically underground or transfer it to other things. This is the process. But the challenge is that the concentration is very, very low. Can we absorb it efficiently? And the other thing is that this geological storage thing is that very easy. Only 3 or 4 countries around the world are engaged in this thing. India, China, and others. For direct air capture, it's difficult for them because the technology doesn't exist at this time. And our goal is to create such technology. Let me take you for the next 10 minutes through my lecture and where you get an impression of what we do. Our process is a very simple process. You take a column. This is the material we prepare. For the sake of time, I won't get into the details of that, but we give a name to start with, call it Lucas. I teach in a university called University. So the process is very simple. Take the atmospheric air any place, including the room. Pass it through this absorbent, which I'm calling Lucas. We get CO2-free air, and then there will be a regeneration part I'll come down to. The question is, does this new adsorbent have any advantage over all others? And this is a very critical one because we have only 400 ppm CO2, whereas flue gas in stack has 100,000 ppm. Okay, so that's the part. So you see, our material started with a parent ion exchanger. Its capacity, it's being used all over the world. 1.8 moles of CO2 per kg. And for our Lucas, which was made out of this thing with some modification, it has nearly 3 times higher capacity CO2 than the parent material. We found information in the literature and we find out the capacity is significantly higher, 2 to 3 times greater than all of the solvents you know of. Not only that, there's another interesting thing I didn't include that its capacity is like this. regardless of the influent concentration. That means when it is 100,000 ppm, it is still 5.1. That means at low concentration, it can capture very, very high amount of CO2. That's the feature. See, I'll not get into the details. I'll just give you one or two highlights. But the other kind of key attribute of this material is, you see, this is Atlantic seawater. After it is exhausted, you can just put the seawater through the column. CO2 comes out as alkalinity, or sodium bicarbonate. In other words, seawater can be used as a regenerant. And seawater can be used as a regenerant. You're asking me, right? Oh, okay. Sorry. So seawater can be used as a regenerant, and you get carbon dioxide converted to sodium bicarbonate. So when it is sodium bicarbonate, you can just throw that straight into the ocean without worrying about without worrying about the geological storage. So this is a very significant new avenue for sequestering CO2, where geological storage is redundant. You do not need geological storage. So this is just one data, plenty of data. But again, when you do this kind of research, you imagine certain things. You have a goal, you dream something. So the goal is, which you are going ahead, is like this. You don't need it in the country. You go to the offshore of Bangladesh, or Barbados, the land of Gary Sobers, So something like that, which is about to sink, underwater. We go there, go into the ocean, put this Lucas column, run it, just take the air, run it through, we get CO2 free, it's captured here, then take CO2, the seawater, pass it through the column, it comes out, and it becomes higher alternative dump right into the seawater, and that also helps reverse. This gradual acidification of the ocean, and obviously we need one that's kind of a little obstacle. We need renewable energy to produce sodium hydroxide to pretreat this material. So this is altogether, this is a self-sufficient process. We capture CO2 from atmosphere, direct air capture, very high capacity, much higher than any other, at least which exists in the body of literature today. You can regenerate that with seawater. That's also very unique attribute of this material. It goes to ocean. You don't have to worry about the essential existence of your geological storage, but we need some renewable energy to get the sodium hydroxide. So this is the broad scope of the process. I'll come back to the same thing because I've taken different problems around the world, and many of you at least look younger than I am, so you'll probably take more challenges. Science and engineering are meant to solve problems, so whenever you see a problem, you take science and engineering to solve it. It's a straight line, you go first straight line, you think that this is great, but nothing in life works in straight line, The chances will fail, you will fail, but if you kind of stay stubborn, keep doing it, then you'll find out, yes, I found the solution, but not through straight line, You have to go through this convoluted path. And for every major significant invention, discovery, breakthrough, it is always through convoluted path. And certain things are, I believe, this is my lesson, very important in order to arrive at that point. You need a touch of humility. That means if you think you are a PhD, you teach somewhere else in a good place, you know everything, it doesn't work that way. So you have to have the humility to learn new things, even from simple people, from functionally illiterate villagers. And the other thing is tenacity or resolve, that I'll not stop until I find the solution. I mentioned about the technology. I think that's our divider. because we do not look at that way. Up until now, technology has been top down, which is called trickle down. Whenever you enter into something, just think maybe kind of a little more deeply. And what I find is there are two ways. You start your research on new thing top down, that is bottom up. If at all possible, go bottom up, start from the foundation. And this is a quote, which is definitely universal, that the gift of a pinnacle is not in the measure of its height, but in the breadth of its foundation. You don't have the foundation, you don't have anything, okay? It will fall down. So try this route. Cell phone, this, that, they're good technologies, but they're top down. You just sitting at the bottom of the pyramid, somebody throws, it goes down, that's how you get it, okay? So this is, with that, I have maybe one more. Okay, I did my due diligence. After 5 years of effort, I wrote a book, pretty big book. I just gave one book to our chemical engineering department library. I have very good memories about that library. This book just got, got translated in Chinese too, so that they can also, a very expensive book, so I do not expect individuals to buy it. But your teachers can take advantage of it. I'll be very happy, and that's what it is about. I hope this book will last long after I have perished. With that, I will stop here. I'll be happy to undertake or entertain any questions, any comments, okay? Thank you all.
Thank you very much, Professor Sengupta. I would like to request Professor Ranjana Chaudhuri to felicitate Professor Sengupta with a bouquet of flower and a memento.
ভাই আমাকে একটা ছবি পাঠিয়ে কপি পাঠিয়ে তো পাই না কোনোদিন সবাই ছবি তুলে যায় so much nice. Thank you.
Thank you very much, Professor Chaudhuri. Thank you very much, Professor Sengupta.
Questions? Yeah, you can always ask me. I'll be here after some days.
Yes. Yes. Yeah, I'm here. Okay. Can I share and make sure that you see? Oh. No, but I don't see it. Yes. Yes. Yeah. Oh, I don't know why it's not working. Okay. Can I share and make sure that what is that? See, yeah, I know. We did it this morning, but my system doesn't seem to work now. No, but I don't see it. Yes. Yes. Yeah. Yes. I don't know why it's not working. No, just 1 second. I will find it. What is that? Yeah, I know. We did it this morning, but my system doesn't seem to work now. No, but I don't see it. Yes. Yes. Do you see anything? Just 1 second, I will find it. Oh. Okay. So you will send me Zoom? Do you see anything? No, I don't. Yeah, I see it on my screen, but I cannot seem to share it. Yes, yes, I have everything. It's just, I, I know, Sudeshna, but my system is not working. Can you send me a Zoom, please? Okay. With my email or? Okay, I'm leaving the. share the presentation. It is disabled sharing. Can you give me the... No, you have to give me permission. Oh, okay. Okay. Fine. Okay. Okay, thank you. Sorry about that.
I consider it a great honor to
You have the full screen, right?
introduce our next plenary speaker, Professor Duigo Kochafe. She is Professor in Mechanical Engineering of Department of Applied Sciences at UKAC. She is an expert in the fields of carbon, anode production, modeling, and optimization of industrial processes, heat and mass transfer, and reaction kinetics. Professor Kochafe is the holder of the UKAC Chair on Industrial Materials, Director of Graduate Studies in Engineering, and responsible of the production in Aluminium Research Center, Regal. She is the author and co-author of around 300 articles in journals, national and international conferences, as well as 161 presentations and posters. I would request Professor Kochafe ma'am to please continue.
Okay. I'll start by saying good morning. It is 10 minutes after 1 in the morning here. Thank you for inviting me. It is a great pleasure to address you, even if it's distance. It's a little bit different topic. I will talk about the partial replacement of petroleum coke with biocoke in anodes used in aluminum production. This is the plan of the presentation. I'll a little bit talk about our university and introduce the aluminum production where the anodes are used and our infrastructure. And I'll talk about the main topic, partial replacement of petroleum coke, finish with conclusions and acknowledgements. First, where we are. Stationary members, this I think. This is Canada and Quebec province, and this is where University of Quebec Chicoutimi is. And it is a mixture between the nature and urban life. Here is the university, and we are part of the University of Quebec network. And in this region, this region is the heart of the aluminum production in Canada and Quebec, and research on aluminum is major in University of Chicoutimi. How do we produce aluminum? Aluminum and actually the forest industry are the two of the most important industries in Canada. In 2020, 3.1 million tons of aluminum were produced, and 90% of this produced in Quebec. Canada ranks 5th global producer and 2nd global exporter of aluminum, including our region. Many of the regions depends on aluminum economically. And there is a big, fierce competition in aluminum production in the world. Quebec distinguishes itself by producing the greenest aluminum in the world because of the hydroelectric power used instead of coal. Reducing the cost of production, decreasing energy and carbon consumption, as well as environmental emissions, and increasing productivity are main concerns of the aluminum industry, and these are all related to the quality of carbon anodes. Here is how the aluminum is produced. Alumina is introduced between the anodes here. These are the anodes, carbon anodes. And alumina reacts with the carbon in the anodes and to give aluminum, which is here, the blue, between the electrolyte and the cathode, and carbon dioxide, which you can see coming here. The air can infiltrate through the cover of the electrolysis cell. By the way, this is called aero process. And it can react with the carbon of the anode. This is called air reactivity. And also the carbon dioxide produced here can react with the carbon anode, which is called the carbon dioxide reactivity. We want these side reactions to be as low as possible because they use carbon, otherwise which can be used to produce aluminum. Industry has to maintain the anode quality in spite of variations in the raw material. We want to have high density because it provides more carbon, low electrical resistivity because it reduces the energy consumption, low air, low CO2 reactivities, which reduces the carbon consumption, and good mechanical properties because we don't want the anodes to drop into the electrolysis cell. And anode quality affects the quality of the metal, operation and stability of the electrolysis cell, energy consumption, gas emissions, and greenhouse gas effects. This is how the electrodes or anodes are produced. We have the raw material here. We call it dry aggregate, coke, and the rejected anodes, as well as the parts of the anodes left after the electrolysis. These are crushed, and certain particle size distribution is prepared. Then pitch, which is a binder, added to the mixer. They are mixed, and anode paste is formed. Anode paste is sent to vibrocompactors to produce green anode. Green anodes are baked, and baked anodes are rolled and sent to electrolysis cell. And we have two laboratories. One is the characterization laboratory, where we can measure the carbon dioxide air reactivities using thermogrammetry. Wettability, I'll talk about a little bit later. Electrical resistivity, density, chemical composition, etc. And this is our laboratory for anode production. We have the mixer and the vibrocompactor, the baking furnace, as well as the coring equipment. And the anodes produced, they have the similar properties to those of the industrial anodes. This makes it easier for us to transfer our results to industry. Wettability. First time the dry aggregate and pitch come together in mixer, okay? And the pitch has to penetrate into the pores of the coke and voids between the particles, and to do that, pitch has to wet the coke. During the baking, pitch carbonizes, and what is formed is pitch coke, and that binds the coke particles and all the dry aggregate particles together. And to achieve this, pitch has to wet well the coke, or biocoke in this case. What is wettability? And when a liquid particle, drop is put on the solid surface, it takes a certain shape and forms an angle theta. This angle theta is called the contact angle. If it is bigger than 90, system is not wetting, pitch will not enter into the coke particles. And it is less than 90, it is wetting. That is what we want. The smaller the contact angle is, better the wettability is. And finally, complete wetting at contact angle 0. This is our experimental system to measure the wetting angle or contact angle. We have a video system and the software to measure the contact angle change with time. And this is the result we get, contact angle versus time. And as I said, this is two wetting contact angle curve. The one with the smaller contact angle represents the system with the better wetting properties. After the background information, now I will start talk about partial replacement of petroleum coke with biocoke. In the aluminum industry, the quality and the availability of petroleum coke has been decreasing. This is due to the increased demand in aluminum production, and the industry is looking for alternative raw materials. As I said in the beginning, Canada and Quebec produces the greenest aluminum. However, it still produces 2 tons of carbon dioxide equivalent per ton of aluminum. So industry is also trying to find a way to reduce this. One of the solutions could be partial replacement of petroleum coke by biocoke. Biocoke is renewable, it has less impurities, and it is emission neutral. Forest industry also has its own problems. There is a decline in the utilization of paper products. Therefore, due to the electronic media, therefore the residue of forestry industry or side products of forestry industry is not used as much, so industry wants to diversify its operations. So replacing the part of the petroleum coke with biocoke will benefit the aluminum industry. It will reduce the environmental emissions coming from this industry, and it is an alternative source for coke. And for the forest industry, it will add value to byproducts. It is a sustainable development and circular economy where one industry uses the side product of another industry. It will diversify the forest products and reduce greenhouse gas emissions for this industry also. But there are challenges. Biocoke has low density, low wettability, high electrical resistivity, high carbon dioxide reactivity. These are all the properties we don't want to have. So that is why it is not possible to make anode just using biocoke. And the general objective is partially replace the petroleum coke with biocoke for reducing the greenhouse gas emissions, but without deteriorating the anode properties. As you have seen, the properties of biocoke is inferior to the properties of petroleum coke. So as soon as you put some part of, you replace some part of the coke with biocoke, the properties deteriorate. When we started this work, we looked in the literature, and there are some researchers, they tried to do this, replace part of the petroleum coke with biocoke, but according to results published, properties of anodes always deteriorated. I think our group is the first one. Finally, we're able to do this. We started with the preliminary studies, and this is the green anode density. This is the green anode resistivity. We want high density, low resistivity, as I told you before. These are the standard anodes with no biocoke, and we saw that increasing the biocoke content in the anode, density decrease, electrical resistivity increase. That's not what we want. And these are done with the relatively larger particles of 125 micron. We decided to decrease the particle size to 45 micron. And finally, by replacing the part of the biocoke, 3% of coke with fine particles of biocoke, we were able to get the properties similar to that of the standard anodes. We said, okay, we solved the problem. Similar for the bake density and bake resistivity with the fine particles, we got reasonable results. We thought we solved the problem. It is great. And then we applied for a grant. We got the grant to continue with the study, to study the other parameters. But we were surprised with the new, when we started making anodes, we didn't get as good results. We weren't able to get the properties similar to standard anodes. It was perplexing. We had the same pitch, we had the same wood particles. Only thing different was we received new coke. So it is obviously because of the coke, and it showed us the raw material can affect this, and it is not always applicable just using fine particles of biocoke. We wanted this to apply to any coke. We should be able to do this with any coke. In our previous studies, we modified pitch and the coke, and we got good results. We improved the quality of the raw material, we improved the quality of the anode. We said, why not apply this to biocoke? Pitch and biocoke, they have some chemical functional groups at their surface. Okay? If these functional groups are compatible, they will form bonds, and the pitch will penetrate into the coke particles and give good density, etc. But if they are not compatible, they will not form a bond, and then the pitch will not wet the biocoke. What we did is we used additive. This additive has also its own functional groups, okay? And functional group of additive can form bonds with the pitch and with the biocoke, and indirectly, pitch and biocoke, they have a link, and pitch can penetrate into the biocoke. That is the idea of modification of biocoke. And the additive should be inexpensive, non-toxic, to be able to use in industry, not contaminate the anodes and not contaminate the aluminum. So we decided to look at the effect of coke type, and because we want to see if with the additive we are able to use, replace the coke, any type of coke. Okay, we use 3 types of cokes. This is high sulfur coke, low sulfur coke, and mixture coke. Industry usually uses mixture. It mixes different types of cokes to get the average properties they want. The blue ones here, they are the standard anodes made with 3 types of coke. This is green anode density. This is the baked anode density. These ones, these anodes, they don't have any biocarbon in it. This is shown here with B0. Just to compare the 3 coke, both for green anode and baked anode, we see that the high sulfur coke gives a better results, followed by low sulfur coke, and the mixture coke has the lowest density. The red ones here, after the density after we add the biocoke, okay? And like everybody else found in the literature, adding biocoke or replacing one part of the coke with biocoke reduces the density. Then we modified the biocoke, as I explained, and we got densities closer to the standard anode for all 3 cokes. If you look at the electrical resistivity, it is similar. We want low electrical resistivity. Now these are the anodes without biocoke. Green anode is before baking, and the baked anode. If you look at the results, again, the high sulfur coke gives the lowest resistivity, which is best, followed by low sulfur coke, and then the mixture coke actually used by industry. Adding biocoke increase the electrical resistivity, which we do not want, and modifying the biocoke again decrease the resistivity. We looked at other properties such as the air reactivity, CO2 reactivity, mechanical properties, and we saw the same thing. I am not showing all the results because of the time limitation. We wanted to see why, the mechanism, so we did an XPS analysis. First, if we compare the three cokes, we see that high sulfur coke has the highest oxygen content, followed by low sulfur coke, and mixture coke has the lowest oxygen content. And high sulfur coke also has some sulfur and nitrogen. This oxygen, sulfur, nitrogen, they are called the heteroatoms, and it is well known that heteroatoms help the wettability of the system. Okay, so this explains why high sulfur coke gave the best properties. If we compare the non-modified biocoke with modified biocoke with additive, we see that again the oxygen content increased with the modification. That means there are more surface functional groups attached to the surface. If you look at the C1s components of XPS analysis, which means the functional groups or the chemical groups at the surface, again for three cokes, for the three cokes, we see that the high sulfur coke has most oxygen and nitrogen containing groups, and the mixture has the least. Again, comparing non-modified biocoke with modified biocoke, we see that the percentage of oxygen containing groups increased. This we can see with the wettability results also. We see that high sulfur coke is wetted the best, followed by the low sulfur coke and mixture coke. Then we looked at the effect of additives. We used three different additives. Excuse me. And we see that this I explained before, the standard anode, adding biocoke, decrease the density, modifying the biocoke, increase the density. Similarly for the baked anode. Here are the three additives we used, A1, A2, A3. We see that the A1 gave the best results, or modifying the biocoke with the first additive gave the best density, followed by the A3, additive 3, and the additive 2 didn't give good results at all. Even the density even was lower than the density when we added the biocoke. If you look at the electrical resistivity, again, similarly, biocoke increased the resistivity, additive decreased. Comparing the three additives, again, we see that the A1 is the best, followed by A2, A3, and A2 didn't do a good job. Resistivity was higher than the standard anode as well as the anode with the biocoke. Again, we wanted to see the mechanism, and we did XPS analysis. We see that with unmodified biocoke and biocoke modified with additive 1, there is a slight decrease in aromatic content. We want high aromatic content because aromatic content increases the density. However, the decrease is very slight, and the increase in oxygen-containing groups are obvious, so that is why the A1 worked best. A3 also gave good results. If we look at A3, the aromatic content decreased a lot, but this is compensated by the increase in oxygen content functional groups compared to the unmodified biocoke. However, if we look at the second additive, now aromatic content decreases too much. It became all aliphatic. Even if the oxygen content is increased, it couldn't compensate for this much decrease in aromatic content. So this explains why A1, A2 gave good results, A1, A3 gave good results, and A2 didn't. And this we can see with the wettability results also. This is green is the unmodified biocoke, and we see that the modified with the second additive has wettability even less than the unmodified biocoque, higher contact angle. Lowest contact angle and best wettability was for the additive 1, followed by additive 3. In conclusion, modification of biocoque with chemical additives 1 and 3 improved the interaction of biocoque with pitch and helped maintain the properties of carbon anodes. Biocoque emits the same amount of carbon dioxide already used by the plant during the growth cycle. Thus, net CO2 emission is zero. They do photosynthesis and they consume CO2, and then when they emit CO2, that one cancels the other. So as I said in the beginning, this greenhouse gas emissions generated by aluminum and wood industries will be reduced by the partial replacement of petroleum coke with biocoque. And also the value will be added to the residue of wood. There will be other options to use the forest industry residue. As maybe you have also saw from the results, we are able to increase the densities, etc. But in some cases, they are not equal to the standard anode density. So it may not be possible to maintain all the properties of anodes. However, there are other factors to be considered. First of all, carbon tax has to be considered. Biocoque is much cheaper than the petroleum coke. Cost has to be considered. The transportation of the biocoque, because during the transportation there is also carbon dioxide emissions, they all have to be considered and economic analysis has to be made. We use always the same pitch percentage, which was optimized for the standard anode. Maybe adjusting this pitch percentage might further improve the results. So we are continuing with the project. There are different parameters to be considered. One is the pitch percentage, and the pitch probably has an effect on that. Pitch can be also modified. So it is continuing. Industry is very much interested. Our partner is ready to make a few industrial anodes and try them in the electrolysis cell to see what happens. So I hope you enjoyed the topic. If you have any questions.
Thank you, Professor Kochafe. If there are any questions. Okay, so now it's time for the tea break. I would like to request all our guests to kindly join for tea that will be served outside. Thank you.
which direction should I point it to? Okay, because small is going to be, it is the next big thing. So I'm, as I have been kindly introduced, I am at the Chemical Engineering Department of IIT Kharagpur. So my lab typically works in the following areas. I'm not going to talk about all of them, it's not possible. So we work on liquid thin films, how a thin film of liquid can have excellent properties in terms of its heat dissipation capability, the high values of the transfer coefficients, and so on. Digital microfluidics, how you could move a droplet to different places by the application of an external force field. It could be electrical, it could be magnetic, and so on. We also work in biomicrofluidics, how you can see a droplet of a blood and what kind of information you can extract. In all these are going to be at the very small scale. We also work in the energy storage, how the dendrites, again, acts a phenomena at the interface between the solid and the liquid, how the dendrites form, how they grow. Can we mimic them using some of the tools that currently are available with us? We looked at crack dynamics. What makes a paint peel off the wall? The cracks are going to form at the walls and so on. What are the viscoelastic liquids? What are their properties at very small scale where the gravity effects are going to be negligible and everything is going to be controlled by the forces, the surface forces, and so on. And obviously, we would try to put some mathematics into it to make sense out of the large, huge data that we create. So from thin films to droplets and beyond, so what we look at the thin films, we look at the region where the three phases, the solid, the liquid, and the vapor are in close contact with each other, how the interfacial forces, the molecular forces start to become important, and what could be their possible applications. And if you look at the droplets, which you see everywhere, they're very, very important, and they are size dependent. If the size is small, then the gravity is not going to be important. The droplet is going to take a spherical shape. And the shape of the droplet is also going to be dictated by what happens at the interface. What kind of force is present at the contact line region that would make the droplet spread, or that would make the droplet come together and form a spherical droplet, all having very important applications, some of which I would touch upon. So the broad applications of the area, okay, can I move to the next slide, please? It's taking too much of a time. So anyway, if I look at how do I control the droplet movement? There are some active control strategies where, as I mentioned, you can have electric field, you can make the two droplet bring together, the two droplet will mix, and there's going to be a lot of diffusion taking place, which actually act as a microreactor in some applications. So think of these two droplets as two chemicals who are going to react. But if you would like to make that reaction taking place much more efficiently, you'd like to reduce the diffusion length as much as possible. And one way of doing that is start with a nanoliter size or microliter size droplet, bring them close together by some external agency, and let the reaction take place in the small confinement. You can do the same with magnetic field. In fact, if you have a large thermal gradient, because of surface tension changes, the droplet will move from the hot area to the cold area. So this is another way of moving the droplet. You can have acoustic waves that move the droplet as well. There are passive ones where this surface is highly hydrophobic. So when the droplets approach this, they will immediately move away from there. So the relation between the hydrophilicity, superhydrophobic on one side, superhydrophilic on the other side, and we see examples of that in, let's say, from a lotus leaf to a surface, and more on that would be presented by Professor Ravibrata Mukherjee this afternoon, so I'll skip this part again. right? Everything you are going to talk about hydrophobicity, hydrophilicity, the contact angle, the surfaces, and so on. So I am putting pressure on him. So can you move to the next one, please? Okay. So this is, in a nutshell, some of the work. I will not talk about all. So from the effect of electric field on thin liquid films, in order to detect some diseases, what can you do using microfluidics? Some protein aggregation. Can you really look at the protein aggregation at the interface and alter the process of the agglomeration of some of the proteins, which have direct consequences for Alzheimer's disease? So what can you do in which the agglomerated plaques on your brain can be disaggregated, disassociated from one another, a lab scale replication of that we try to do. The colloidal film crack dynamics that I have discussed about, this is the one in which I'll spend some time. Can you look at the drying droplet of a blood and predict is there any specific disease? So that's what we are going to talk about. And there are some molecular dynamic studies which I will not discuss over here. So these are electroplating studies. So what you see, this is about 0.1 micron. So we have some advanced optical ways to measure the film thickness and how it changes while you apply an electric field. It's going to be its dependence on voltage. What happens if I apply an electric potential? So an oscillation in the film can be brought about by applying an AC field. What could be the effect of that? Can I use this as a coolant in electronic systems, where the liquid is going to move towards the hotspot on application of an electric field, evaporate from there, extract the heat, and then come back and flood the portion once again? So this kind of oscillatory movements can be brought into action by the application of an electric field. Same thing can be done for magnetic field as well, which I'll not discuss this because of time. About the blood one. Maybe that and one more problem I will discuss today because it's already 1:20. So the question that we are going to ask ourselves is there any effect of interfacial energy when a droplet of blood dries? What would it lead to? And whether or not can a dry droplet of blood be used for the prediction of some specific disease? And the disease that we have in mind is thalassemia. You know that the problem of thalassemia, the full-blown thalassemia, and the carriers of thalassemia. So I have done this work in collaboration with Calcutta Medical College, with their head of the hematology unit. And what she told me is that every time they have thousands of blood samples and they have to detect whether or not someone is going to be a potential thalassemia carrier, which would then go through a rigorous tests and which would take days in order to come to a conclusion. So we are looking at alternatives. And the problem of thalassemia are well known to us. So we have done certain studies and we took samples from Calcutta Medical College, which some are known carriers, some are not, healthy and carriers. And at some point of time, we took 100 samples of them, and we told them that to give us 50 carrier samples, 50 healthy samples, but do not tell us which one is what. So that's the blind study that you have to do. So the experiment that we have done is pretty simple. We have a droplet of blood, let it dry, and then look at the cracks which automatically form. Cracks are the ways for the droplet to reduce its stress. Whenever a droplet dries containing some suspended materials, there's going to be formation of a stress. And this stress can be released by the formation of a crack. The same reason why cracks appear in paints. When you paint and it's not proper, then cracks would appear. That's nature's way of releasing the stress. So we are looking at the cracks that are formed in these two types of cells. And what we found is something very interesting. For the healthy ones and for the diseased ones, the crack lengths are different. But that's just a statement. You have to prove that how different they are going to be. Okay? Are they statistically significant in terms of the difference? So we looked at different ones which contains the thalassemia carrier and which are healthy. And what we found is that significantly shorter radial cracks for the carrier ones. So there is a definite trend. So we have done the blind test then, and we, can the next slide be please? Next, click one more. One more, okay. So what we found is that if the crack length is greater than 800 microns, then it's going to be normal. If not, it's going to be carrier. But that's, again, just an observation. So we have to think about the science behind it. Why would the cracks be longer for healthy and shorter for the carrier ones? So what we did is we looked at the stack of the red blood cells in a dried droplet of blood, and we count the number of cells in that. Without going through the slide, let me explain. That would be faster and easier. So the red blood cells, when they are stacked one above the other, this one, which has only the cell at the top and at the bottom, there's going to be cell-cell interaction. The cell, which is closer to the substrate, is going to have cell-substrate interaction. So we wanted to quantify these cell-cell interactions and cell-substrate interaction. And what we found is that there is going to be significantly different forces that are present between a carrier one and a normal healthy one. Next slides, please. Next. Right, so this is how it looks like under ACM. That what you see, the disc-like shapes, they are essentially the red blood cells. Next, please. Fine. So the physical interactions are essentially the attractive van der Waals forces and the repulsive double layer interactions. We do not have to know all this. It's that when you bring two surfaces together, there is always be an interaction, an attractive interaction because of van der Waals forces, the formation of dipoles and induced dipoles. And there's also going to be, if you bring them very close to each other, there's going to be a repulsion. So it's the balance of these two major forces which would dictate what is going to be the interaction in energy between the cell and the surface and between the cell and the cell. So we computed this, and what we have found is that there's always going to be a major difference between the carrier and the healthy. So the interaction at the interface, the cell-cell interaction, would tell us significantly, scientifically, that they should behave differently. So what we were observing experimentally has a theoretical basis. Next, please. Next. So there is a way by which the volume of the crack can be related to all these interaction energies, and the volume of the crack for the healthy one and for the carrier one is essentially proportional to these interaction energies. Next, please. And next. Right. So when we calculate purely a theoretical exercise, this ratio is about 1.3. And what we have found in our experiment is about 1.2. Those of you who have worked in biological systems, you understand that 1.3 and 1.2, if you get between experiments and theory, you should be very, very satisfied. So that's what we were. So we could see some difference, and scientifically, we did prove that there has to be a difference. So that's one of the major achievement of this study in locating the carrier ones. Next, please. Next. So there was a PhD student and a BTech student like some of you, and all of you are interested in making some app. right? So I challenged them that, okay, come up with an app in which you will take the picture using your cell phone, compare it with a database, and come up to tell us, measure the crack length, and tell us whether this specific sample should require further probing in order to make sure that it's not a carrier. So that student came up with the app, and which he has innovatively named as ASAP. And so you take the picture and you can give some idea about what it is. Next, please. Next. This one I probably may not have time to discuss, but just a little bit of idea of what happens during the recharge of a lithium battery. There's going to be something which happens at the solid electrolyte interface. So the lithium ions come and try to deposit on the surface, but due to the electromigration and diffusion, combined electromigration and diffusion, these kind of dendrites will start to form. Next slide, please. And as the dendrites form, they are going to block the path of the incoming diffusing lithium ions, and there could be a thermal runaway as well. So it's always advisable to create a strategy by which you can minimize the formation of these dendrites. Next, please. So we were looking, if you can run this. It doesn't run, doesn't matter. Next slide, please. So I was going to show you how the dendrites grow in real time. But anyway, I can go to the next slide. So we were looking at these formation of these dendrites, and in a cell that we have designed, a very simple mini cell, where on a copper where this kind of dendrites were growing. And we were making different strategies. Especially what we have found out is that if you alter the charging potential, instead of always applying a constant potential for charging, if you apply a sinusoidal wave or an off and on circuit, the dendrite formation is going to be lower. This we have observed experimentally. But then we wanted to find out what's the theory behind it. Can it be explained by theory? Click on that and it should work. So for that case we were looking at different simulation schemes. And the schemes that we have followed, in which it's going to be a random walk model for the molecules, where the molecule is going to be diffusing in any direction, and there is going to be an electromigration. So when there is an electric field, it's going to move towards the electrode, and when the volt potential is switched off, then it's going to have only a diffusion. So there is going to be competing electromigration and diffusion. So there's going to be an electromigration vector, velocity due to the electromigration, velocity due to the diffusion. Go to the next slide. Velocity due to this electromigration, and the resultant is going to be the movement of the lithium ion onto the surface. So we have done extensive numerical. Next. Again, next. All right, so we have done a coarse grain modeling. I will not go into the details, but what we have found is that our coarse grain modeling, when we make the two systems equivalent, it's extremely difficult, because what's happened in your double layer, which is close to the solid liquid interface, that's of the order of microns. If you look at the movement of the ions during that time, the time scale is in picoseconds or in microseconds. The length scale there we are talking about is going to be in nanometers. So how do we bring our experimental results and compare them with the theoretical modeling? So again, we have done some mathematical exercise that I will not explain. Next, please. And what we found is that what you see, these are equipotential lines, and the formation of these. Next slide, please. Not this one. Okay. The last one for my presentation. I have skipped many in between. Some out of necessity, and some I was forced to. But anyway, this last one is about a surface that we have on this. And I have put a droplet over here. The idea is that the droplet, if it evaporates from the surface, because there is a small heater below this, if the drop evaporates, it's going to take the latent heat and keep the surface cool. Now, you all know that most of the electronic packaging problem these days deal with a very small area. A small heat is produced because of very small current passing through it. As a result, you have to extract very high heat flux. The amount of heat is minuscule, but the area is so small that the heat flux is going to be very large. So how do you do that? One of the ways of doing that is to use the latent heat of vaporization. That's the highest amount of heat transfer that you can get. So if you could take a coolant droplet to the spot where it is going to be, where you are going to have a hot spot, let it evaporate. Enclose it in a system where the vapor will go and condense somewhere else. And due to the application of an electric field using digital microfluidics, you can make the droplet, condensed droplet, again to the same spot. So this kind of thermosiphon, which goes on as a microheat pipe, which goes on all the time as long as you have a heat source, that people have tried. We have done that as well. But we thought it would be much more interesting if I bring the droplet over here. This one mimics the hot spot. And instead of just letting it evaporate, if we could mix the liquid in between. So the droplet sits on the surface, it's evaporating, but I also have internal circulation. So if I have internal circulation, obviously the heat transfer coefficient will be more. That we all know from our heat transfer. So how do you induce circulation in such a system? Next slide, please. Next slide. Okay. So you have to, if I can create a surface wave, then obviously this change in the surface is going to penetrate in here as well. So there's going to be something similar to that at some depth, and therefore a circulation will generate. How do we do that? I'll come in the next slide. But how do you model that? The way to model this thing has came from a system which is very, very large. We are talking about a microliter sized droplet, but the idea of modeling this came from ocean waves. When waves are generated in the ocean, not only there's going to be undulation at the surface, those are going to penetrate below as well. So below also there's going to be a wave that we do not see at a lesser amplitude. So how did people do that? And we have used that same concept for making this oscillation droplet and connecting it with more extraction due to mixing from this. Next slide, please. Now, I would like to show this video first. So this is a droplet, this is an electrode, and this video should work. It worked in the other one. So when you apply 300 volt. The whole point of this slide is the video. If you take your pointer over here, it should, over this region, you should see an arrow. Yes, okay. This is what, when the delay time is 200 milliseconds. Can you play it once again? This left side. Okay, so it's changing. So there are surface waves which are forming that you can see if you really look at it frame by frame. Reduce this time and run this once again. And you can yourself see that by changing the way you control the off time, on time, you can really have it dancing around, but stuck to the same spot. And the proof of that, this is the hot spot. The red refers to very high temperature. When you have this kind of an oscillating droplet, this becomes green. So this means it's at a lower temperature. So just bringing a droplet onto the surface, letting it evaporate, the temperature is still high. Bring it, let it oscillate, create surface waves over here, and what you see is substantial cooling. There are a lot of physics involved in it, mathematical treatment, which I will not go through right now. So I have covered some of the subjects, some applications. One is with blood, the second is with battery, and the third is with cooling. All are micro scale phenomena. All happen because of something is happening at the interface that is changing, that is forcing the process to behave differently. Probe deeper, and you get an understanding from the basic sciences that there are wonderful things for chemical engineers to do beyond so-called chemical engineering. So as you were speaking about 2021 and beyond, 23 and beyond, probably this can be another path for some of you to take. So if I could excite some of you in that, especially the students, I'd be very, very happy. Next slide, please. These are some of the publications which I have tried to report in here, and the next slide. These are my students. Some of them are faculty at different IITs, and they are currently also working with me. I must thank my sponsors, Department of Information Technology, Intel, Department of Biotechnology, ISRO, and IIT Kharagpur. I have active collaboration with Purdue University, with the Mechanical Engineering Department, RPI, which is my alma mater, Calcutta University, and I must mention Professor Debashish Sharkar, with whom I have ongoing collaboration and who has helped. Together we have learned many new things together. The Calcutta Medical College, and currently, very recently, we have started another collaboration with American University of Beirut. And finally, I hope that I did not, the next slide that, I will not show it. The next slide that I am going to show you, I would be very satisfied if you do not behave like what you see in the next slide. So if that is the case, then I'll be satisfied. Next slide, please. That last slide. So that's my last slide. I hope you are still awake. Thank you. And I guess the question answer can be during the lunch session itself. Thank you again.
Thank you, Professor Dashgupta. I would request Professor Shrudeshna ma'am to kindly felicitate sir. With this, we end today's plenary session, and now I would request all our eminent guests to join us for lunch at the guest house, and all the internal students are requested to join for lunch in the chemical engineering department itself. Thank you.
বা অরুন্ধতি দিকে কল করে নাও না।
অরুন্ধতিকে ফোন করতে হবে?
হ্যাঁ,
আরে
কারণ মেলাতে
বেসিক্যালি জানি, কারণ খাওয়া হয়নি তো না, সব জনের একটু সমস্যা হয়ে গেছে। কেউ অরুন্ধতি ওখানে নেই, কিন্তু আমি জানি না কোথায়। আমি দৌড়াতে দৌড়াতে এলাম।
হ্যাঁ, অন আছে, দেখে নাও। করে দেবো জিনিস হয়নি স্টার্ট করে দেবো So, good afternoon, one and all. My name is Sreyoshi Borua, and I have Aishwarya Das with me to co-host this session. On behalf of the entire Department of Chemical Engineering, we would like to extend a very warm welcome to all the distinguished delegates, respected professors, honorable dignitaries, and the students. On this keynote lecture session 1, an invited lecture session of International Conference on Chemical Engineering, Innovation and Sustainability organized by Asia's oldest chemical engineering department. Now I would like to pass over to Aishwarya to introduce our first speaker for the session.
Good afternoon, everyone. So the first keynote lecture will be given by Dr. Ravindra T. Goti. Dr. Ravindra T. Goti is currently the Dean, Alumni and Corporate Relations at IIT Bombay. Prior to this position, he was the professor in charge of the IIT Bombay Research Park Foundation and also served as head at the Department of Chemical Engineering and the professor in charge of continuing education and quality improvement program at IIT Bombay. He also holds the institute chair position in artificial intelligence and machine learning. He earned his BTech and MTech degrees from IIT Bombay and a PhD from University of Alberta in 1995. His research interests lie broadly in the process systems engineering and green engineering, that is modeling, optimization, control, and fault diagnosis of process systems, sustainability in industrial practices. Dr. Goti has served as a visiting professor at the Department of Chemical Engineering, University of Alberta, Canada, 1997. Department of Chemical Engineering, University of Wisconsin, Madison, 2003 to 2004. And the EECE Department at Washington University in St. Louis. Dr. Goti has published over 150 Scopus Index papers and has 9 US patents to his credit in various areas of process system engineering. He has guided over 60 PhD and MTech students in their research at IIT Bombay. Dr. Goti is a fellow of the INAE and a recipient of several awards, including the Canadian Commonwealth Fellowship by the Government of Canada, 1991 to 1995. Lavraj Kumar Memorial Award for Promotion of Industry-Academia Interaction, July 1998 to January 1999. Manudin Applied Research Award in 2006. Hardelia Award for Excellence in the Basic Chemical Engineering in 2009. He is also an associate editor of the IFAC Journal of the Process Control and guest editor for the Control Engineering Practice. He serves on several technical committees of IFAC. He has also been an active consultant to the industry in India and abroad. I would now like to call upon stage Dr. Ravindra Goti to please convey his lecture.
Thank you. Good afternoon. I already lost 3 minutes, I guess, in that introduction. I think this is just a quick introduction about myself. AI and ML, as the buzzword stands as of now, artificial intelligence and machine learning, has been cyclic. It's been visiting us in a cyclic manner. Way back in late 80s, early 90s, we had AI coming in Avatar, which did not sustain for a long time, but then it has come back now in a more powerful avatar, given that there are several advances in computing infrastructure and computer science, cognition, and the like. So it's now becoming much more of a promising technology, but we need to be very careful, and therefore I have titled my talk as Whether AI, whether it is artificial intelligence or whether it's augmented intelligence. And the message that I would like to pass on in the 20-minute talk is that please do not consider AI as a panacea solving all problems that you have at hand. Especially for the students, don't forget your domain. Domain is even extremely important, in fact, more important than the use of AI and ML tools, as I will show you in a short while. Okay? So very quickly, this example basically illustrates the complexity that we have when we are making decisions, be it in the design, let's go one step back in the fundamental discovery, in the design, in the commissioning, in the operations of various chemical processing units. You typically have a lot of uncertainty, and you have very poorly known cause and effect relationships. For instance, in fundamental discovery, you have a hypothesis and you want to verify that hypothesis. As you go towards design, you would like to know how the design parameters are affecting the eventual efficiency of the design. When you're doing operations, you want to make safe operations, you want to make high productivity operations. To be able to make these kind of decisions, typically there is a lot of uncertainty in the decision making, and AI/ML is a very nice complement, is what I want to emphasize, over and above the basic domain knowledge. So that's what I would like to show you first from an operational context by using this example. This is, as all of you can recognize, a boiler example. This is where a boiler converts fuel into flue gases, which goes into a boiler, where steam is generated, that goes and drives a turbine and the like, and you generate power. Now, obviously, when you're looking at this application, stepping back, what you want to do is you want to have essentially a high efficiency combustion. But if you are going after that objective, you typically don't know what are causing the efficiencies to be not highly efficient, A. Now, B, you don't even know what high efficiency is. Typically, you just look at operating data and you say, this is the average level of operating efficiency of this combustion process. You want to basically define, redefine, re-establish your targets so that you can actually go towards high efficiency combustion. Now, what is the uncertainty that we are coming up with? Typically, if you look at ML as a layer, machine learning as a layer, it is advanced statistics. You have lots and lots of data. And typically, there are these 5 V's that are associated with the data: volume, velocity, veracity, variety. These are the 4 V's. And of course, eventually, all of that must contribute to value, which is the 5th V. Right? So if you look at some of these measurements, you have the fuel quality sensors that are coming at a relatively infrequent rate because it has to go into a lab's analysis. If you look at when a flame burns, there are acoustic sensors that give you a sense of how the flame is burning, and the frequency of that acoustic sensor can tell you about the efficiency of burning. Thermal sensors are in the environment of the flame. You could have flame images. Now, these deliver images at a particular frames per second. You need to be able to process that. So, flame parameter extraction. You have to look at emissions and see how well your fuel has burnt, right? So all of these give you some information about how your combustion is happening, but not a complete picture. So what you want to be able to do is you want to combine all of this information together to develop some kind of an assessment of what the combustion quality is, which is bringing together all of these measurements. Now, just having this is not sufficient. Right? You need to go one step ahead because our eventual objective is high efficiency combustion. You just have a sense of what your combustion quality efficiency is as of now, right? You want to promote, you want to increase this. This morning we had a very brilliant lecture by Professor Juma where she talked about a digital twin, right? Now a digital twin is precisely that, as the name suggests, it's a twin which basically mimics the operations of the plant. So if you have a combustion quality assessment, you can take all of this data along with the combustion system model, adapt and update that system model so that it stays current with the current scheme of operation, right? You need to be able to do that very quickly in real time. And then you want to use advanced optimization tools, which means you will query the combustion system model, which is now a replica of the actual plant. You will query this in various what-if scenarios and try to come up with ways that gives you a high efficiency combustion. Now, to be able to do this, there are 2 things that you need to do. One is, when you do this assessment, you set a benchmark. A benchmark could be the best seen efficiency, but how do we know that we can't exceed that? the digital twin will give you the theoretical limits of what your benchmark should be. So you could either have a practical benchmark or you could have a theoretical benchmark, and you would then query using the advanced optimization and control tools, try to push the operation as close to the benchmark that you have established as possible. That gives you high efficiency combustion. Now I talked about the 5 V's. You can already see some of them here. This is an infrequent measurement. This is a frequency measurement. This is a regular measurement about the temperatures. This is an image. This is emissions, which is composition. And now you want to bring all of this together, which is some kind of an exercise in sensor fusion, right? So putting all of that together gives you a sense of what is the kind of diversity that you're looking at and what is it that you need to do to your artificial intelligence and machine learning algorithms to be able to make smarter decisions that promote high efficiency combustion, which means even you want to approach the theoretical benchmark as closely as possible. Okay? So when we do this, obviously there are several things that come into picture. One is discrimination between an average performance and a best seen performance, querying your system model to see what is the theoretical best limit, and then making appropriate advanced control, advanced optimization decisions to be able to push the operation as close to the. So what are we looking at when you're operating a chemical plant? We are really looking at a digital tsunami. You can see there is an experienced operator and there is a trainee operator. In a regular firefighting exercise, the trainee has to be trained to operate the fire hose. But what we are staring at now is bits and bytes of data that are coming at you at speeds that are much, much faster than you can process. And so really, tapping into a data stream is like drinking water from a fire hose pipe. You really have to have really sophisticated algorithms, both on the machine learning side as well as on the artificial intelligence side, so that you are able to make fast and quick decisions to be able to operate your plants better. Where are we now? We are looking at basically digitalization, which is converting what is analog into digital, digitize, and then digitalize. What has spurred its growth? I talked about the second cycle of AI and ML. There have been advances in computing, sensing, of course, all we know, it's becoming more miniature with 5G communications and platforms and the like. And what impact does it bring? It brings in a lot more connectedness, integration, safety, productivity, and of course, the aspect of operational excellence. Okay? So I'll not go, given the time, I'll not go into too much of details of this operational excellence. I'll just quickly tell you what we are aiming at. So what is digitalization? It's basically science and technology enabled business transformation that basically converts current or partially digitized approaches to vastly improve industrial practices. This is on the sensing part. Now over and above that, the improved connectedness between different entities, aspects related to coordination and cooperative decision making that essentially promote safety and compliance, and of course improved productivity. So really digitalization is generation. Generation essentially means where do you incorporate your sensors, how do you generate the data, transformation of the data. Now this is the most critical step in AI and ML, which is transforming it into a new domain, a new space where viewing the operations in that space gives you more clarity about what's happening in the plant. And of course, finally, analysis of the data to aid in agile and optimized decisions. I'll just skip this in the interest of time. We are really going towards from IoT to industrial IoT, Industry 4.0. In fact, we have a wish list for 5.0 that talks about cyber physical systems, massive personalization, and of course also going towards Industry 6.0. I'll just skip this. Now let's come to the fundamental question of what is AI. Okay? AI in the operational context. Of course, it can be looked at in a design context. It could also be looked at a fundamental discovery concept. But from an operational context, it's basically discovery and purposeful utilization and exploitation of meaningful patterns. So you're basically trying to see what the plant is trying to tell you through its data. Okay? At the faster scale, of course, we were always doing this in process control. So what's new? The new thing is basically this data pyramid. We are looking at converting data to information, information to knowledge, knowledge to wisdom, which is what you see here. Basically, data is discrete elements coming together. It gives you a raw pulse of the system, which one could use for process control. As you go and aggregate the data, you essentially get information in terms of signatures and trends. As you organize this information, you get best operation templates. You remember I talked about the benchmark, how close you can get to the benchmark and the like. Best operation templates can be generated. And when you apply this knowledge, not only across, the methodology, the workflow, if you apply it to the same units, but also across the different plants, you basically get consistency in best practices. Okay? So the moral of the story is, of course, in an operational context, listen carefully to your data. It has a very interesting and useful story to be revealed. This is stretching across all the domains that I mentioned: discovery, looking at design, deployment, and of course, fault detection and diagnosis. So where are we now in the AI area? Of course, we are data rich but information poor, as we say in several platforms. This table basically gives you where we are. And a typical chemical plant, although here I have said exabytes, we are going towards zeta and yottabytes. Okay, it generates a huge amount of data. You want to make sense from this data. And if you look at processing volumes of this kind, you really want to delve into the data. And the phrase that is typically used is rescue the data from the graveyard, because otherwise it is just lost there. Can we rescue the data from the graveyard, generate a lot more knowledge that will help us to operate our plants better? So that's the objective. As I said, at the discovery, at process development scale, you have a lot of data that you can generate at the lab scale, at the pilot scale, at the plant scale. Can we basically extract out useful information at each of the scales, and more importantly, transfer it to the higher scales so that you are able to retain the knowledge? So at the different phases of a product life cycle, can we leverage that, represent what is known, emphasize what is unknown, and then adapt and update with data generated in the different phases of the development. So again, coming back, the main message is listen carefully to your data, interpret the signals into meaningful information, build knowledge using the information, and evolve safe, improved, optimal, and compliant operating practices. Again, as I said in the beginning of the talk, what I want to do is basically project this in a way that it's not completely first principles agnostic. Chemical engineering is very, very important. You have to know your chemical engineering quite well. I'll show you a very quick example of that to be able to deploy AI and ML approaches in the operational context, likewise in the other domains, other phases as well. So typically, what kind of information do you have? When you're talking of artificial intelligence, you have only data. But we are now migrating from what's called as artificial intelligence to augmented intelligence. So what are we going to augment the intelligence with? We are going to use these three sources. Of course, measurements are there, which is what the traditional understood AI context is. But we also have a lot of first principles knowledge. None of this is complete. Neither the models are completely known or accurate, neither are the measurements complete in terms of the system at hand. Of course, you also have mismatch, poor understanding of your model. You also have noise with respect to the measurements. What is it that you can do to exploit knowledge from all these three sources, which is first principles knowledge, knowledge from the measurements, and of course, a relative assessment of how accurate each of those are? How can we bring all of those together? And there have been several approaches in chemical engineering that talk about variety of scenarios. You have accurate models, noisy measurements, noisy model, noisy measurements, model partially known, noisy measurements, and so on. Different variants of these three cases. There are several approaches that have been proposed in chemical engineering literature. What we understand is only this as AI, but it's not restricted only to this. We really can look at the entire spectrum of possibilities that can be applied. So let's look at some of the typical objectives. Of course, one is we talked about the volumes. We have an artificially inflated measurement space. We like to do dimensionality reduction. We want to discover patterns. For example, we said high efficiency combustion versus an average efficiency combustion. How do I differentiate between them? Can I look at the patterns of data and say that the next time this pattern occurs, it is an average efficiency operation that is fit to be, decision making has to be done to push it towards high efficiency. So discovering patterns and data clusters in the data, building soft sensors. Many times quality itself is an inferred entity. It's an inferred, you can never measure quality, you can only infer quality. So how do you build soft sensors, which are like hardware sensors, but they are based on algorithms? Can we have soft sensors? Can we generate, there is a lot of noise, can we filter them out? Can we generate reduced variance estimates? Can we use models for prognostics and diagnostics? In fact, as I speak, I would like to do a little bit of publicizing of one of our research at IIT Bombay in the biosciences department. They have come up with a simple blood test that can predict whether a patient is likely to develop dementia, Alzheimer's, and Parkinson's. A simple blood test which is some kind of a prognostic. right? Diagnostics is basically after it has occurred. If you have prognostics, you can take early decisions. So it can basically do a lot of, AI can do a lot of prognostics, signature mapping and the like, diagnostics, to see post-mortem analysis, and of course continuous performance assessment. I mean, you have to keep learning, you have to keep updating your models, you have to keep updating your templates so that you push towards. So let me just skip this in the interest of time, since I have only 20 minutes. Let me just quickly take you to an example. Okay, just skip this. I'll have the slides, of course, but let me take a simple example of this. Okay, now there is an algorithm so let me go back here. Yeah, there is an algorithm in fault detection and diagnosis called principal components analysis. This is used in other domains as well. Typically also in, when we are doing fundamental structure property relationships in materials and the like, it's used there as well. I'll just take you through a simple example here in the interest of time. This is a low density polyethylene reactor. The reaction happening is N monomers of ethylene become polyethylene. The operating conditions are 150 degrees centigrade, high pressure, and degree of polymerization 10,000. Now, by itself, it's a well-established process, but there are several undesirable side reactions. For example, you can have hydrogen production, you can have methane production that's associated with high exothermicity, explosive reactions, and of course, economic loss of the ethylene. Okay? So to be able to detect this early, that the LDP is actually getting into a runaway reaction, you can do the post-mortem analysis, but it might be too late. The question is, can we detect that early? Can we deploy some prognostics? And what we did was basically looked at first principles models. But as I said, first principles models themselves are incomplete. You also have measurements. What are those measurements? Typically, the flow rates, the initiator flow rates, unreacted ethylene product flow rates, and the like. If you're able to measure them, you have these. Now, what is it that you could do? You could do two things. You could say, let me develop a AI/ML algorithm, which is artificial intelligence machine learning algorithm. If you do that, you're just going to use all of these measurements and trying to detect when a runaway reaction is happening. Turns out that that is too slow in the sense that it gives you a very delayed prognostics of what's happening. Instead, what we decided to do was, let's try to use our chemical engineering knowledge and just try a simple steady state enthalpy balance. So what we see here, there are heating, there are cooling elements, and those should close to zero. If they don't, of course, because of measurement noise that you get from those measurements, there is going to be an error, and you could put control limits on that error. Now, what's the problem with this equation? There is component enthalpies that are dependent on temperature. There is significant uncertainty in the relationships between specific heat and temperature. So how do you solve the enthalpy balance in the presence of uncertainty? Okay? You could basically then use a very advanced mathematical model by defining the uncertainty in the parameters of the dependency and then try to do an uncertainty relationship. The other advantage that you can do is you can use an ML-based approach, an advanced ML-based approach, principal components analysis, recognizing that if you rewrite that equation in a slightly different form, you have temperature measurements and you have some of the flow measurements, and you basically can then close this material balance to zero. If you do a little bit of a rearrangement, you could write this as in this form, where the alpha contains the uncertainties in the heats of reaction and the Cp values, and the rest are basically functions of temperature. And now what you do is you apply a simple principal components analysis, exploiting the first principles knowledge as well as the data-based approach to principal components. You basically do a PCA on this, and when you choose the smallest component, I'll not go into the details of this, but if you look at the slides, basically what it means is establishing the threshold for safe operation. These two steps essentially do that. And so long as the operation is within the thresholds, you're fine. When we applied this on actual plant data, here is what it was able to do. Of course, there are some false alarms, but about 3 minutes before the onset of decomposition, the pattern recognition algorithm was able to tell us that there is a runaway reaction that's being initiated, which eventually will lead to an explosive reaction, and so appropriate correction steps could be taken to take care of this. So what I'm trying to say here is that one needs to migrate from artificial intelligence, which is purely data-based. Of course, advanced cognition algorithms, advanced algorithms based on computer science theory do exist, but data is only as much. You can only do as much with the data because, as they say in statistics, if you torture the data sufficiently well, it will confess to anything, right? So you have to be very careful about what you're going to do with that data. You have to augment that data with first principles knowledge, like what we did here, to be able to make sense and make inferences that make sense from an overall perspective. I'll just run through, in the interest of time, through a few other examples. Data clustering, I'll just skip this again. I'll just show you some examples of data clustering here. This is a data which was an artificially contrived data where you can see that there are two clusters in the data. One is the blue and one is the red. Now you can think that blue is a high efficiency combustion and red is an average efficiency combustion. Now in the original measurement space, I can't discriminate between the two, right? Because there is an overlap. I can't differentiate between the two. But if I now use advanced artificial intelligence algorithms, scaling, and taking the data into a different space, you see that when I do that transformation, it resolves the two clusters into two distinct rings. And now the next time I have an operating point, I can clearly classify whether it belongs to the red envelope or to the blue envelope, right? So this is what discrimination can do. And this is an example in healthcare where you have different types of cancer, and the same scaling and transformation basically looked at, for example, if you see the aggregate, the pink points here, they are distributed. When you apply this transformation, it all coincides into a single point so that there is no overlap between the red triangles and the pink asterisks. So in that manner, once you are able to separate out the clusters in the data through appropriate transformation, you are able to discriminate and then be able to say that, the appropriate information is present in each of those clusters. We applied it on a high purity distillation column. Again, here there is a difference in the time scales. You can see the 4 classes of dynamics. One in which the gain is low, the time constant is 62, but if you see here the gain is relatively high, but 4 times the time constant. You could do a lot with this kind of an information to do advanced process control. I'll just again skip this in the interest of time. Pharma manufacturing is one of the important applications. Typically in pharma applications, there is a lot of batch rejects that happen, which can be realized only when the batch is complete and they do a QC. Okay? If you can actually do an analysis of how the batch is progressing with respect to time early during the batch. So if you are able to predict the final batch quality, even when the batch evolves with respect to time, there are 2 things that can happen. One is the batch release times get shortened. They are providing a real-time batch qualification, and you are minimizing the possibility of a batch going out of control. You can initiate appropriate mid-course corrections to correct the batch quality. This is something that we did jointly with an industry for a life sciences manufacturing example, where you see the performance index on a scale of 1 to 9, 9 being a golden batch, 1 being a poor batch. And on the average, most of the batches fell around 3. The final antibiotic titer, the final batch duration is something that's of importance to the manufacturing company. These are being predicted in real time. I'll go for further, again, very quickly in terms of achieving operational excellence. Suppose you do go into the archive and you mine the data and you find that there is, for example, in the combustion application, you basically want to have a high productivity at a very low specific energy. Okay, so this is the best or the golden operation. This is an average batch, and for political reasons, I don't want to say ugly, I want to use the word good. Okay. Now, if I have this as my data in my archive, if I exploit first principles and I use AI and ML approaches, my target would be to push it more closer to the golden batch as possible, so that I eventually narrow down the variation. For example, if this is the limit for operational excellence, in the ordinary case, I would have a spread away from the limit. When I apply AI and ML tools, I go closer to the limit, but with a lot narrower variation, which is what operational excellence is all about. Okay? So this we applied to control loop performance monitoring as well, to aspects related to model plant mismatch detection. This was something that we tried for a kerosene hydrotreater unit in Suncor Energy, and we were able to make sure that those models are tuned well so that we get improved closed loop performance. They could also be used to detect interactions, non-linearities and the like. For example, some of the advanced ML tools can actually go towards being able to detect, for example, if I have a control valve stiction, if I have a non-linearity in the operating behavior, I could use higher order statistics such as coherence and bicoherence to basically detect the presence of non-linearities and then be able to take appropriate control actions. A quick plot of what bicoherence looks like in advanced statistics. So you can see that if it is linear, you don't see those peaks. If it is non-linear, you start seeing those peaks. And that helps you to detect the presence of non-linearity. Okay, so again, keeping look at the clock. Okay, so maybe I'll just spend a couple of minutes on this. I don't know if I have, yeah, I do have this example. All of you might realize that this is perhaps the most complex operation in a petrochemical unit. You basically have the fluidized catalytic cracking unit. It's a gigantic scale operation. If some of you have not seen this, this is like a 5-storied building where catalyst slugs get thrown up and down. Catalyst slugs are typically of the type of Maruti car getting thrown up and down in a reactor. Regenerator blows off the coke that's deposited, and then there is a looping here. So the catalyst comes down here and again rises back here. So when this happens, its control is typically a very complex task. So you could look at it as a one single gigantic problem, or you could decide to split it up into 2 simpler problems and the like. And how do we do this, and how do we detect that kind of decomposition that is needed? Again, looking at the plant signatures and be able to detect the presence of interactions, and how do we want to break it up. This is going towards the controller design, one step ahead to operational excellence. How do we deploy efficient control structures that are manageable, which is, what you're doing is you're dividing and conquering. You're dividing this entire plant into several subunits. When you do that, of course, there is going to be an interaction. How do you effectively account for that interaction and promote the same control performance that you would get from the entire plant? That is where AI and ML approaches can quite significantly help. So let me just summarize in the interest of time. Some of the interesting problems, we already talked about combustion monitoring on boilers, gasifiers, IGCCs. Environmental systems, emissions and carbon credits, typically when you measure the environment, let's say at 1 kilometer or 2 kilometer altitude, what you measure is an aggregate of several emissions that are happening locally. Now, how do you assign what you measure to each of those sources? So identification of blind sources, that is one of the problems associated with AI and ML. Patient health monitoring, this is something that is very, very important. I'll give you an example of the Parkinson's and the related. But how do you bring in first principles knowledge about disease and how it transmits? We had an excellent example of pandemic. I won't say excellent, but a pathological example of pandemic. If you really want to do patient health monitoring, now digital health is becoming an increasingly important aspect. Ayushman Bharat Digital Mission is one of the important initiatives of the government. There, a lot of AI and ML can actually come because of the heterogeneous responses, context-aware sensing, of course, social issues, and the diversity in the measurements. Engine health monitoring, every single time, every millionth time an aircraft takes off, it lands safely. Accident rates are pretty low. Engine health monitoring is an extremely important aspect. In fact, the flight duration is like a batch process in chemical engineering, right? It takes off, cruises, and then lands. So this is like a batch process. How do you make sure that batch after batch you produce consistent quality is a problem in chemical engineering. How do you make sure that a flight, when it takes off, lands safely in an energy efficient manner is a problem in aviation. So you look at that from an engine health monitoring perspective. Causality detection, now this is the post-mortem. This is an extremely difficult problem in causality. What caused a particular scenario, especially in the complexity of measurements, the maze of measurements that you have is not a straightforward problem. This is some of the emphasis points in AI and ML research to do causality detection. Again here, if you just look at data, it's not sufficient. You do need to augment data with as much first principles knowledge. As I said, neither the first principles knowledge is accurate, neither the data is accurate. You have some sense of their inaccuracies, some sense of the noise in the measurements. Can you use all of that information together and make smarter decisions in AI and ML? So that's what this talk is all about, and I hope I'm able to convince you that augmented intelligence is the way to go over and above AI and ML. Yeah? Thank you very much.
Thank you, sir, for your insightful presentation. I would like to request the audience to address any question or queries regarding this presentation.
That segregation that you showed in the cancer context. So it is segregation of what measured parameters? Is it like an image of the diseased tissue?
It is blood tests, the gene expressions. The gene expression.
So you have to identify the PCAs and do the segregation.
Correct.
Fine.
Yeah.
Sir, actually there is no clash between the AI tools and the expert knowledge, I believe. I don't know whether you will agree, because how the tools will be used, it's absolutely tool. And there is the very ideal area of the collaboration between the computer scientist and the domain knowledge experts. Because it's a very high power tool they are developing. So unless the other domain knowledge people don't use it successfully, then the development of these tools will be meaningless. For example, one of the area we did actually, that's a power plant power prediction on the basis of some minimum input parameters for the by using artificial neural network. And interestingly, one set of data was from India, another set of data was from Slovenia. If we go for the first principle model, the whole input data, if it is wrong, nothing can be done. But we found out that when during the redundancy, we switched over to other parameters, and still we can make the continuous monitoring process by using the NN model. So obviously it's a very good, there is no clash between the domain knowledge and the AI.
Let me just re-emphasize what I was saying. The central thing in AI and ML or any decision making is knowledge representation. Now, knowledge comes from those three sources that I mentioned, models, measurements, and a relative understanding of how much the inaccuracies are, right? Now, when you represent the knowledge, if you can quantify it with the level of uncertainty that you have, you can use first principles knowledge, you can use what data is trying to tell you. The best of the algorithms that processes the data will tell you something. The best of the model solving approaches, optimization approaches will tell you something. How do you basically use that, aggregate that information together to make a smart decision is what it's all about. Augmenting the knowledge is what it's all about. There is absolutely no conflict. You're absolutely right here.
Another issue, sir, if we just put the first principle model into AI, what you are telling, that augmentation of knowledge, then the problem will be the real-time applications may be sometimes difficult. Because any model means you have to calculations and other things.
So let me point you to an emerging area of research called physics-inspired neural networks. That is one area, but in general, physics-inspired knowledge representation. Neural network is just one way of representing knowledge. This paradigm basically represents, in terms of a solvability of, when you say real time, obviously you are alluding to solvability of the models. When you look at training these neural networks using the physics embedded in the neural network, it is certainly takes it takes about the same time that you would use for a database neural network training. However, the physics-inspired neural networks is more representative of the fidelity of the cause and effect relationships than a neural network based on data alone. So, and that is one thing. The other thing is it is solvable also much faster than if you use a first principles based model. Yeah. So
then we can discuss offline.
yes,
yeah,
certainly.
Thank
So
you.
I would refer you to PINN, physics inspired neural networks.
And lastly, why the expert system failed?
Oh, expert system has not failed. Expert system has come in a new avatar here. It's never failed. I don't think it has failed. Any other questions? Okay, thank you.
So, thank you for your questions. I would like to request our head of the department, Dr. Roger Chakraborty, to felicitate Dr. Goody.
কে দেখছিল এটা
So moving on to the next speaker, we have Professor Dr. Rajdeep Bandyopadhyay. A short biography on him. Professor Dr. Rajdeep Bandyopadhyay is a professor in Chemical Engineering Department of IIT Bombay. He started his career as an assistant professor at IIT Kanpur before joining IIT Bombay. Okay. So like his bachelor's degree was from Jadavpur University, Kolkata, both master's degree and PhD from IISc Bangalore. Subsequently, he did his postdoctoral research in Israel and USA from University of Utah and University of California at Los Angeles. His current research uses both experiments and mathematical modeling, focusing on using the principles of colloidal and interfacial science to link the synthesis structures, dynamics, and properties of nanomaterials. Okay, moving on
if you
to...
don't mind,
Yes.
because there are a lot of talks. So, good. Thank you very much. Thank you to the department. And I like to walk while talking. Huh? That will be too close. So, okay, thank you very much. It's a homecoming and pretty excited to meet everyone, my teachers, fellow new students, past friends and new friends. So a quick pop-up quiz post lunch. I think many of you know the answer. Any answer? So I mean, it's not compulsory. To get into the talk, I thought just do a quick fact check. So this is Michael Faraday. About 150 years ago, he said, no matter what you look at, if you look at it closely enough, you are involved in the entire universe. Now that's a very profound statement, but after listening to Professor Gudi, I want you to come down from the holy grail of AI/ML down to the earth and just a drop of water. So we apply this principle to a drop of water, and my plan is to tell two sub-stories, and if time permits, how much time do I have? I have an hour or so. Do I have an hour? No? Okay, 20 minutes, okay. So within that, I'll tell you two sub-stories and maybe 1 or 2 points if the time permits. So inspired by that, as I said, we look at the drop of water. A small step. I can't say I solved world's problems, but hopefully others working like us will solve the world's problem. Now, if you look at a drop of water, you know, it's a 1 ml in volume. By the way, this picture is from internet, but I forgot to put the credit here. It has about an Avogadro number of molecules, right? That's a lot. And but if you think of it, even one E. coli cell, you know, if it goes inside, it multiplies inside our gut and causes disease, and especially children get killed, right? Diarrhea and all. And that's bacterial contamination. And then there are other contaminants like arsenic, fluoride, which are pretty much everywhere, especially northern, northeastern belt. And we have heard an excellent talk today morning about arsenic removal. So if you look at this calculation, out of Avogadro number of molecules, you have to detect, you know, a few molecules with you. Why I will tell you that? So our problem, as I tell today, is to detect molecules at a small concentration. Why? Because you have a very strict limit on drinking water. If you want, about 10 parts per billion of arsenic molecules is what we can drink. Of course, nobody wants to, but that's the threshold limit. And 1 ppm of fluoride molecules that you can permit. Okay, so if you can do the maths, pretty simple, is that you have to detect 1 fluoride molecule in 25 million water molecules and 1 arsenic molecule in 4 billion water molecules, okay? So you span from ppm to ppb, you go from detection capabilities of millions to billions, okay? Tough job. And we want to do it faster, on the spot, and not take the water sample to the lab. Of course, those technologies are there. So that's one goal. And once you have done that, you want to remove those nasty elements to make it safe for drinking. So I'll illustrate this theme within the time scope. with one example. That's why I say 2 sub-stories. From each of them, we'll look at maybe arsenic data a little bit, because we had an excellent discussion on arsenic today morning, and removal of E. coli, and at the end we'll connect them together. Okay, so now we work on nanoparticles, so we want to use it to our advantage because we have some idea, some experience. So if you think of it as a particle, this is a spherical nanoparticle, and nano, everyone knows, is something which is small, you know, a couple of nanometers to maybe about 100 nanometers in diameter. So the idea is it will go and pick up arsenic, if you like, or fluoride or E. coli, and so on and so forth. And then this is the cartoon that I'll use later. These are the E. coli cells. These are micrometer long, so really micro to nano. So these are like small dots to these big giant cells. And nevertheless, we power pack these particles with something which will go and hit the cells, cause some small damage, like you can see these small dots, which are really the nanoparticles, you know, kind of hitting the bacterial cell wall. This is the true E. coli cell, and then creating some damage and doing some reaction. So in this, we will take advantage of our classical chemical engineering understanding of, adsorption and reaction, right? So we will see how that can synergize my killing process to make it fast, because you want to have water which comes out very fast. You want to hold your bottle of 1 liter of water and have it filled in 1 minute, if you like. So that's the goal, of course. We haven't gone there. So quick primer on nanoparticles is, again, the sphere, just to get our facts right. We are interested in specific surface area, which is the surface area of the sphere per unit mass. Okay, so specific surface area is important, that is meter square per gram, rather than just surface area, because you want to use a lot of surface area in a small amount of volume, because we want to have it like on the spot, portable kind of device. So just meter square is not enough. So meter square per gram is specific surface area, and that scales, that quantity, specific surface area, scales inversely to the diameter of this sphere, the diameter of the nanoparticle, which already you know is couple of nanometers, right? So I just given an idea that if you go from micrometer size particle, okay, 10 to minus 6 meter, to nanometer size particle, 10 to minus 9 meter, you go from 2 meter square per gram, which may be the surface area of this table, to 2000 meter square per gram, which is the surface area of our field in front of our department, right, the football field. Okay, so that's one point. This is very fairly well known to everybody. The other point is chemists, material scientists, and we borrow some techniques from them, has enormous understanding of making these particle surfaces functional by doing some chemical and physical functionalizations, which makes sensing and treatment both specific, because they can hook on to those molecules of interest. Okay, so that's the basic outline. Now, so let's get into the first story quickly. These are India, and these are arsenic contaminated area, and of course this is just India specific, but of course Bangladesh and other Southeast Asian countries and other places in the world also. There are, as I said, there are of course techniques, atomic emission spectroscopy and other sophisticated laboratory-based techniques where you can measure at ppb level. But but if you want to do it on the spot, map these regions in the field very fast in a day, many measurements, then you need to have something which is non-toxic, fast detection with no interference, because there are kits like these kits, commercial kits, but they use mercury bromide and other chemical components, and evolves for arsenic gas because it tries to take arsenic, which are not, of course, desirable, and it has a long response time of 30 minutes of reaction because it is a two-step reaction. So we want something simpler. One idea which I'll quickly share is we took a gold nanoparticle. Okay, why gold? We can discuss that later. Basically, there is a phenomenon called specific surface class bond resonance. Okay, which allows us to take advantage of gold, and we put some vitamin B12 molecules out there. Okay, they are specific to arsenic, antimony, and selenium in the same group like we saw in the morning. But here we assume that there is no selenic and antimony in the water. We are talking about arsenic. So they go and latch on to these arsenic molecules. So these red arsenic molecules, or arsenic ions, to be specific, 3 and 5, actually 3, which is more toxic, latches on to these functional groups, the blue Y-shaped vitamin molecule, methylcobalamin, basically what we take as a vitamin supplement, and makes this gold decorated, the pink gold particle. Now once this happens, this arsenic is valency 3, so it holds on to these 3 particles, and basically what you're seeing is a single gold particle getting transformed into an aggregate of gold particles. So this is the central theme. This is a cartoon to make you believe that there is 2 images we have. This is single gold particles, transmission electron microscope images, about 10 nanometer in diameter, actually precisely 8 nanometer diameter. This blue, this black distribution, and when it aggregates, it gets into these larger, wider distributions of 20, 40, 60, up to 100 nanometer. So you see this aggregation from here to here, that is captured in the size distribution. Of course, you can't do microscopy on the field, you can't do light scattering on the field. This is in the lab, but the proof of the pudding is in the eating. So you see, when gold aggregates, there is this peak shift in the surface plasmon resonance, which is an optical process. For that, you have to just shine a UV light, it passes through the solution, and it gives a peak. Okay, it turns out that this absorbance peak, because of that aggregation, monotonically increases with the concentration of arsenic in the range of our interest, which is 0 to 100 ppb. And mind you, we say 10 ppb is a drinking water standard that you would like to have. So you really want to say whether this water sample is below 10 ppb or above 10 ppb, which is fairly possible here. It's kind of a linear response. Then it saturates out as expected, but that level can be increased by changing, reagent ratio. So I'm not going into that. We have that. The most other important thing whenever we talk about a sensor, the first is response, linear, good, fine, matches with the lab-based spectrophotometer, red and black, all that good, but selectivity. So as you see here, there are a lot of other things in water, iron, copper, calcium, zinc, heavy metals, whatnot, and nitrate, sulfate, phosphate, other inorganics. They don't give any response. This is absorbance versus concentration of other these things about 1,000 times more. ppm level concentration also, they are not giving, ppm level concentration is not giving any response, whereas a 10 ppb arsenic, okay, gives this high red bar, which is the absorbance plotted here. And if you add all this into that arsenic, still the response remains same. So that means what? There is much less chance of false positive, false negative if you talk in terms of, COVID detection. Okay, so to prove that, we did some field study. This is a little bit old, but nevertheless drives the point home that we can have 1.3 ppb arsenic in a lake water, this Powai lake in front of our building out there in IT. And, sorry. Okay, so if you have 1.3 ppb arsenic as detected by our instrument, by ICP-MS, which is a Crow equipment, gives 1.18 ppb. So good enough for us because it's 10 ppb, below that, holds that promise. And also if it is above that, 17.4 ppb, not a good water, which is a dirty river inside Mumbai city because of industrial pollution, Mithi river it is called. The 17.4 ppb turns out to be 18.60, so that's good. And we have of course done others, but it tells you the point. Okay. Now I'll cut the story short because I want to go to the second sub-story. That the point is we therefore could assemble all this colorimetry, spectroscopy inside a box, 3D printed in our lab, some basic Arduino electronics, and then did it for fluoride, chromium, iron, etc. for a single handheld sensor this much size. We have now gone into a little bit bigger but still portable, where you can, like a fan regulator, select one of these 4 knobs and turn this knob like a regulator, and you can select basically different metals and the display comes out. This is the optics part where the water sample goes in, and it does in 4 minutes. Okay. And then we went over and did some work with electrical engineering people, and this is just as of this month, my students went to Kozhikode and we made this device that was handheld on the field. This is remote wireless water monitoring station. So what you are seeing here is the internals. This is on the lake, we have placed it in Kozhikode. And basically it is sampling water from the canal or pond, and these pumps all made by the students in-house, and that is able to fill these sample bottles. This is pH measurement, temperature measurement, and some of the other chemicals that I mentioned. And then the optics is built here, so spectroscopy, the colorimetry, and data generation, and remote transmission of the data. So it's still 2-3 field trials we have done, and like any device building, it's a long journey. So we hope to reach there sometime. So both on field and handheld. Okay. Now let's get into switch gears. I have, I think, 10-12 minutes. So that's perfect. So now suppose you have detected these things, right? So whether it's heavy metal, arsenic, fluoride, or E. coli. We have not done E. coli sensor, much more tougher. But you want to remove them. And some of the points that becomes important when you want to remove, whether it's filtration, adsorption, reaction, etc., is you want to do it rapidly again. Okay? You want to have high reactivity of the system. It has to be stable and long lasting, and it has to adhere on a host, because I can't throw nanoparticles in the water. It will all flow out in the system and it will not work. Like the device that I showed you on field or in this, I can't go and replace it every day. It has to last at least a month or so. Okay, so and we later we developed some membranes, etc. So one question is how to pack these nanoparticles or whatever adsorption media or sensing media you're using, which is nanoparticle for us, onto delivery support systems like substrates, membranes, films, and because they should be immobilized, right? Then it will be long-lasting, self-sustaining, etc. Again, the summary slide to tell the story up front is we took help of carbon, activated carbon, which is nothing but coconut shell, available a lot in South India. We worked with a company called Filtrates in Bangalore many years back. So they used to give us sackfuls of activated carbon, which they make from So on that, we put these nanoparticles. You see these tiny dots, white dots. This is just the nanoparticle as it is. This is the same nanoparticles thrown onto the carbon. Well, we literally don't throw. We do some good chemistry, take care of that, so that they are not aggregated, but sitting nicely, like this part of the auditorium. And we don't want this part of the auditorium like this, because this empty part is not value addition for us. So we kind of try to make it fill. But there is something else, there is some black hole kind of thing. Okay, so that's not a black hole, but if I go to the next. So if you see, there is a lot of such black holes, because this carbon is made just by, as I said, take coconut shell, do an anaerobic process, and get the carbon and activate it, so that's steam activation. So it makes a lot of pores, and these pores are healthy, because these pores are what is responsible for removing your odor causing, taste causing, color causing contaminants to go. But carbon is a source of food for the bacteria, so it cannot take care of the bacteria. For that we are doing these nanoparticles, which is supposed to kill. And which ones we are using? We are using silver and copper. Pretty well known people. We have used silver copper utensils forever. But silver has been known and researched on, but copper has not been done much. So that's why we focused on copper. So again, mundane things like nanoparticle size, 5 nanometer, etc. But the message is that the E. coli will not go through this, because this is a small hole, about a micron or less, whereas our E. coli are 4 micron long. So we want the particles on the surface. Then only it can contact the water that is flowing past this in the filter medium. So this is what our domestic filter blocks are this, which are carbon particles and which are bonded with the polymer to hold the pack, filter pack. And we put these nanoparticles on that, on the outer surface. So when the water flows through, imagine this is the filter column, it nicely comes in contact with these particles. And what does the particle do? That's the question. Okay, so this is what they do. Now, this is 3 panels for us. This is silver particles, on the carbon. This is copper particles on the carbon. And then we went ahead and did silver and copper combination. Okay, out of curiosity, serendipity, and little bit pre-planning, both. I'll tell you why. So silver, remember this adsorption reaction, classic example in chemical engineering, we study to accelerate carbon dioxide absorption, we add amine, right? So we take away the rate limiting step. So here we find that only silver takes 7 minutes to make these dents on the E. coli surface, and 15 minutes to after which the internal reaction happens. So what silver does, it releases some silver ions, goes inside, does free radical generations, okay, and those free radicals interfere with the DNAs and RNAs, whatever they have, and does the intracellular reaction, which basically blows up the cell, and that's what you want. But the copper, you look at it, it does that in 2 minutes, so much faster time scale. So adsorption and pit formation is what we call. This first step is faster by copper. Silver is rate limiting there. The second step, the reaction, the silver is faster. I'll show you more quantitatively. So we thought that if we combine this in some intelligent way, then we can synergize. Synergize means you don't take half of silver and you take half of silver, half of copper in mass. Okay, so you're not adding extra metals or extra functional material, same total functional material, just distribute the mass into two halves, half and half, and then you should be able to get some synergy, meaning some acceleration in time scales, so that you see that is what we did. Only silver took 25 minutes, only copper took 10 minutes, only combination took 8 minutes. So that's a 25 minute to 8 minute, 3.5 times, flow rate improvement. That translates to 3.5 times higher throughput, because you want to hold the bottle of water and get very fast, right? So this is a proof. We put some fluorescent molecules which signifies proportional to the cell life, and the fluorescence intensity goes as time. So if you see the only silver line, that is the black line, see that 20 minutes there is nothing going on, because it takes for silver 20 minutes to form the pit, which is like opening this door. Silver comes and opens it. Suppose this room is empty, we are all waiting outside. Silver comes, opens the door, that takes 20 minutes. So till 20 minutes the cells are healthy, there is no fluorescence activity. As silver comes in, the silver ions in literature, there is proof the silver ion diffuses faster and reacts. So we thought, okay, that's what's happening in 20 to 25 minutes. Of course, we don't have a data point here, pretty difficult experiments. So that many can be done. So that part is very fast. So for silver only, this is the rate limiting. Okay, like only absorption is rate limiting for CO2 removal. And you look at only copper, the red line pretty much starts in the beginning, like the image showed. This copper forms peak very fast from the beginning itself, 1 or 2 minutes. And reaction, of course, continues as ions diffusing copper ions, and it finishes the job in about 10 minutes. So silver opens the door, comes in, copper opens the door, silver comes in, and silver reacts faster inside. So together, when I put half silver, half copper, the red and black, you get this enhancement. This blue and the brown lines, they do it in even shorter time. So this is called synergy. It's not an additive effect, that both together are. This is synergistic effect. One is helping the other. So the overall time scales shrink down, and that's what we have. So like any good experimentalist, we try different ratios, and we find 50-50 is good, cost-wise better, and of course they require very little, so that's not a botheration, but still. Okay, so the end of the story is here, that only silver we get a rate of 1.6 liter per hour, silver copper we get 5.3 liters per hour, and we ran it for many days and weeks continuously and achieved those targets. And latest version of that equipment is this, is on the lab test, 17 liter, this is just as of last year, and 17 liter holding tank. You dump the water for 1 day, cooking, drinking, whatever, and gravity driven system, no electricity, no power. There is this column of silver, copper, impregnated carbon. The water comes in, goes through bottom, gravity driven, right? So it goes through bottom and flows up. So there is no channeling, no bypassing, perfect contact, the whole bed is used. The breakthrough is much later, after a few hundred liters of water. So it's of course going on further. Now I'll skip this. We did the same thing for membrane. We put for do the same job and impregnate the particles on membrane surface. So that idea is taken forward just in a different context. So there are other adhesion and strength issues in membrane, which we addressed. Now, this, just to complete the circle, I said, we did arsenic. In that case, this work I can't share all the details because it's with the company Toray in Japan, so we have confidentiality agreement. But just to tell you that, okay, carbon, hard solid on the nanoparticle and membrane, soft polymers. Now this is fibers on which also impregnation, some other particles which does the job. So after treatment, the fiber looks like this. You pack it in a column and arsenic containing water becomes arsenic free. So this is a cartoon by my Japanese colleague who made, so I can't add more as per our agreements, okay? But trust me, we have done something which is good. But I can tell you it is adsorption plus reaction, not just adsorption for removal of arsenic. Because we distinguish arsenic 3 and 5, and arsenic 3 is more dangerous but difficult to adsorb. Okay, just to cut the story short, then we went into other forms. I'll just show some pictures. These are other particles which we can design with pores. This one single particle, a lot of pores, we can put material inside that, and second nanoparticle which are good and does some drug removal, dye removal. So different architectures of overall particle. The second catalytic particle inside the pores, radially arranged pores, gives a better catalysis rate. We can discuss in detail later. Then rod-shaped particle, oval-shaped particle, very unique. And we see oval-shaped rod-shaped particles gives much better. So the one theme which is emerging from these later slides, which I can't discuss in detail right now because of obviously you want to go to the next talk and Ravi is smiling at me. So I need to give him space. That there is a new thing which I am thinking of, which is shape-induced chemical reactivity, which I think has not been done by anybody. So if there is good result, which we have initial inclinations, then we can discuss next time. So after all this, we take a step back and read this line. If you have a minute, you can, all of us know Alice in Wonderland. So Alice is encountering the cat. So I don't know whether I'm Alice or whether I'm cat. You can decide. Alice says, would you tell me please which way I should go from here? The cat is a sage cat. So it says, no, that depends a good deal on where you want to go, which is applies to all of us. Alice says, I don't much care. So the cat says, it doesn't matter where you want to go. It's a very profound statement. Then Alice adds a footnote. I don't care where I want to go as long as I get somewhere. I just don't want to do a Brownian motion out there. I want to go from target A to target B. Then this is the final bottom line, which is, oh, you are sure to do that if you only walk long enough. So we are just trying to walk long enough. In the sensor domains, it is about 5 years with 2 years in between. In water treatment, 2 years, 10 years. So we want to understand this filtration column. I couldn't resist showing this. I drew it, so please take a minute. So this is the filter column. This is the carbon particles. This is the copper silver nanoparticle on the carbon, which is doing the job. The water is flowing downwards up there. As it is doing, it is contacting the black colored copper and silver nanoparticle. The E. coli coming in contact with that and flowing out. So you see, it's flowing through a narrow channel in the packed bed. Okay, and if you think these narrow channels are of micrometer dimension, and since Sunanda already explained to you microfluidics, so we took this inspiration and said, okay, we'll design a microfluidic experiment which will capture this narrow channel flow between these big carbon particles, decorate the walls of the microchannel with these nanoparticles, black nanoparticles, throw in the E. coli and see what is the single cell E. coli dynamics with these nanoparticles, because a single cell study gives us much more information rather than an ensemble study in a packed bed. So the idea is to improve the performance of the packed bed by doing a single molecule or single cell study in a microfluidic channel. And then we understand a little bit about E. coli dynamics, so we can do that. So just to tell you, I'll stop here with this, just playing this video. There is nothing much to see because the room lights may not allow. This is the E. coli cells which are tagged with green fluorescence. So we are seeing as they flow through those microfluidic channels, which is mimicking this packed bed. And we want to do the kinematics on these individual cells, and what is their velocity, direction change, whether the nanoparticles drive them away or the cells are attracted. Of course, they won't like to go there, but unknowingly are they going, or they are going because of a chemical gradient, which we want to enhance our performance, because we want the particle cell contact much more than random flow will allow. Okay, so I will just end the last slide with the title. the appendix. I want you to see this, because this work, all that I get to present is because of hard work of all these students over almost 8 to 10 years. Pritam did lot of work on the E. coli, the decontamination. Akshay Patil, he did the device design for the water treatment. Angira did also microbiology. Swapnil Shankar did the sensor work. Boe is from Torre. Deepa and Sukesh did some of the catalysis work, which at the end, the shape dependent performance, and we can be reached here. Thank you very much.
Nanotechnology is currently an attractive field in the research to the scientists all over the world. Thank you, Professor Bandyopadhyay, for your informative lecture in the field of nanoscience. Now I would request the audience to please address the questions to Professor Bandyopadhyay. Any questions from the audience?
Yes, so as I explained, from silver, which we did many years ago, we could go 3.5 times more rate by the synergy, which is 5.5 liters per hour. So for a 16-liter water requirement of a day, it will take about 4 hours, which is reasonable, because you dump the water from a source and cook it, and 4 hours. This needs to be changed. As I showed in the breakthrough, that it lasted about 400 liters of water, which is not enough, because ideally it should last at least 6 months to a year. So we are still working on that to improve that time scale of recharging, but there is no loss of silver or copper out from them. It is only the ions which are going on. So we measure that, and that is within the drinking water limit of silver and copper. It's not exceeding it. But yes, the breakthrough we want to do. So that's why we are still Alice, we are still not the cat. Oh yeah. Okay. No, so for arsenic it is not silver and copper. That is for polite. For arsenic it is a combination of two metals. One of them is iron, the other one is another metal. Again, please excuse me, I can't share it because I'm still not allowed to by the confidentiality, but it's a dual metal. So one metal does the oxidation of 3 to 5 and another helps in absorbing. Again, each metal is tailored to that particular job of either absorption. But yes, you're right, the arsenic will stay there, okay, but it will stay as arsenic 5, which is less toxic than arsenic 3. Arsenic 3 is more toxic, but yes, arsenic 5 is also toxic. So disposal of that, yes, it has to be, I don't know, for CO2 people talk about underground storage, so why not for this, the concrete tank and put it so that it doesn't leak out. But the amount is very tiny, but yes, it's still not negligible. That part we have to deal with. But yeah, because otherwise removing in half a minute from 100 ppb to less than 10 ppb. So which is, the kinetics is very fast. I couldn't show that.
Thank you, Professor Bandyopadhyay. Now I would request our head of the department, Professor Raju Chakraborty, to felicitate Professor Bandyopadhyay. Moving on to our next session lecture, the next keynote lecture of the session by Professor Robibroto Mukherjee, who is presently a professor at Department of Chemical Engineering at IIT Kharagpur. He has obtained his BE from Jadavpur University 1994, MTech from IIT Kharagpur 2001, and PhD from IIT Kanpur in the year of 2007, all in chemical engineering. He joined IIT Kharagpur in the Department of Chemical Engineering as an assistant professor in 2009. Okay, yes, actually he is a well-known scientist and professor, so I would call him.
Good afternoon, everyone. My sincerest thanks to the department, the head of the department, and other colleagues, other faculty members in the department for getting me. It's really, really very, very satisfying to be part of the centenary celebrations of the department. Also, great to see several of my juniors. Juma is sitting here, my former teachers, Kajridi is sitting there, Rajdeep Da, one of our idols from student days, colleagues across the country. And most importantly for me, I'm also giving this lecture, since I am in the academic world, so these people I keep on meeting, I'm giving this lecture in front of my first boss, Dr. Amar Ranjan Ghosal, who is a distinguished alumni of this department, 1971, and my colleague Dev Kumar Dotto. So that really makes it very, very special. Sorry for missing out some of you. From the morning, we have been hearing some of the most outstanding lectures, but for me, at least, the theme that is most important, that is something I have highlighted in blue, green. Is it blue? Yeah. So it's more of a centenary celebration for the department, and I thought that I will not talk too much deep into science or the type of research that I do, but one thing, and particularly aimed at the students and colleagues across disciplines, most of you have noticed that almost all the lectures are on very advanced topics, which are apparently not something you study in your undergraduate curriculum. And amongst the students, there is a general perception, yeah, these things, what's the point in reading all these things? You don't do it. Even if you do research, you are either doing physics, or you are doing data science, or you are doing biomedical engineering. So I'm going to talk about something very, very simple. Rajdeep Da made a mention that nanoscience everybody understands. I assume that everybody does not understand nanoscience, and I'm going to delve a little deeper into what exactly is so special about the nano length scale or nanoscience, which all of us think that we know. And as chemical engineers, we also probably think that nanoscience, I ask undergrad students, what is nanoscience, what is so special? And the immediate answer I get, the surface to volume ratio starts increasing. I will go deeper and try to make you understand it's not actually that, there is something more. And many of the effects, even in our undergraduate curriculum, which dominates at the nano length scale, we actually learn as chemical engineers. And therefore, across the globe, you will find a lot of people who are working in material science, nano, and allied areas do come from chemical engineering background. My senior colleague, Professor Sunanda Dasgupta, actually made my life much more difficult because he talked about, he's one of the most outstanding teachers of the department, and he talked about the beautiful science that happens at the microfluidic length scale or at the micron scale. I will go 1 or 3 orders lower and try to make you understand what happens there. So a note of thanks, firstly from our batch, 1994. Chanchal Mandal, who is a faculty in your department, is from the batch, and Manaswita, who is the next speaker from IIT Bombay, is also from our batch, so that makes it very, very special. And also on behalf of the chemical engineering department at IIT Kharagpur, I thought we should thank, because several of our colleagues and former faculty members, here is a list of names who are currently faculty members at IIT Kharagpur, who all did their graduation at some point or the other from this department. Professor Sunanda Dasgupta, time flies actually. Professor Sunanda Dasgupta is now the senior most alumni of the department. I am also, I think, the 3rd or 4th most senior. And here is a list. I took this picture, no offenses, because it's not a current picture. So I think when I visited here during Kajridi's headship 2016, I took this picture. And we were students, were here from 1990 to 94, and we were very lucky to see a whole lot of these people out here who have, I understand, defined and shaped the department in the right way. When we were students, I think Professor G.K. Biswas and Shamal Chanyal were the head of the departments. But anyway, and so a quick outline of the talk. And the talk that I'm going to give is what exactly is so special about the nanoscale. Let's start off with something very practical. Any guess what is this? I won't waste much time. So under a quick microscopic image I took day before yesterday in my lab of a human hair. And depending on whether you use the best quality parachute nariyal tel or not, the size or the diameter of a human hair is somewhere between 50 to 70 micron. So I just wanted to give you a feel how small is nano physically. So basically, if you are talking about 1/10,000th of a human hair, you are roughly in the ballpark of 5 to 7 nanometers, right? About 1 lakh, you are sub-nano. And if you just compare from the bottom-up approach, one inorganic molecule, typically the size is an angstrom. So 1 nanometer is roughly 10 molecular length. Of course, polymer molecules can be much longer. And roughly you are talking about something. So Rajdipda also made a statement that it's 2 nanometers to about 100 nanometers. So what sort of length scale is sort of considered to be this nanoscale? So just a quick feel, 1/10,000th of a human hair is something like 10 nanometers. That's something I wanted to tell you. This slide might be common to at least my colleagues who are from academia. So what is so special about nano? One of the things is these are some semi-crystalline quantum dot nanoparticle, same material, cadmium selenide. Their sizes are different. Rajdipda actually works on these type of systems. And if you sort of illuminate them with some UV light, they emit different colors. So what happens is there is a beautiful word which one can take from chemical engineering thermodynamics. Nanoscale is a length scale where intensive properties becomes extensive, or properties that are typically not dependent on size, they become size dependent. And that's why you see all these beautiful phenomena. What actually is the physics? So if you start making things smaller and smaller and smaller, the band structure starts changing. So you have this valence band, conduction band, which determines whether something is an insulator or a conductor or a semiconductor. The structure itself starts to get changed. People who are into hardcore nanotechnology, device electronics, they focus a lot on this particular aspect. It's well understood. So please do understand, one take-home message for today is nanoscience is not only surface to volume, there is something more. There is another interesting aspect of nanoscience which is slightly overlooked, I would say, and it is also the length scale that is dominated by the intermolecular interactions. Now, what are these intermolecular interactions? These are van der Waals forces, basically the van der Waals forces, or even the polar interactions like hydrogen bonds. So what are these? These are, as Professor Dasgupta also mentioned in his talk, these are induced dipole, or dipole-dipole interaction, most significant being the induced dipole interaction, which is omnipresent, which is present everywhere. Some of you might be knowing about this so-called 612 potential or the Lennard-Jones potential. What does it mean? So even Rajdipda talked about, Professor Dasgupta talked about, so if things are very far away, there's some sort of an attraction when they come closer, and if they're very close to each other, there is a repulsion. So that's exactly what is captured. For most of the engineering applications, we actually focus more on this attractive part of the van der Waals interaction. Okay, maybe I'm telling, so it must be present there, but question to ask is, do we as chemical engineers know about it? Well, one very interesting manifestation of this is surface tension. Now, what is surface tension? You have a large block, and you are cutting it into two halves. So you are supplying some energy from outside. Now what is this energy essentially doing? And again, one answer I get, it is breaking bonds. Well, actually it's not breaking bonds, because if bonds are broken, there is going to be some chemical reaction. Suppose you are cutting a block of butter, there is no chemical reaction. So all it is doing is, you are creating a new surface out here by simply overcoming this interaction between these molecules. So this is the manifestation of surface tension. And I would like to highlight that probably in our school days, we started talking about surface tension and viscosity in the same chapter in general properties of matter. But as chemical engineer, we fell deeply in love with viscosity and completely neglected surface tension. Right? That's not the case. Surface tension is also omnipresent. And as you go down in length scale, with Professor Bandyopadhyay talk, Professor Dasgupta talk, surface tension becomes more and more important. Fair enough. But as chemical engineers, do we appreciate or at least talk about the effects of these interactions? The answer is there are far, far more important examples in chemical engineering which are entirely dependent on this interaction. For example, vapor pressure. For example, boiling point. For example, the critical temperature. They are all manifestation of this interaction. So most of you know probably alcohol has lower boiling point, or organics have lower boiling point as compared to water, which has polar interactions. Here is the secret. For most organic molecules, it's only van der Waals interaction. For something polar like water, it's van der Waals interaction plus the polar interaction. Undergraduate students, I see some students, you probably, in your thermodynamics, one of the first things that you learned is the van der Waals equation of state. In fact, that is where the word van der Waals come in our curriculum in a very strong way. If you remember the functional form, there are many who will remember. So we have this so-called pressure correction factor in chemical engineering textbooks, right? P plus A by V square. Now, I just showed you an equation where the strength of the van der Waals interaction is 1 by r to the power 6. And now what is V? V is volume, and it is nothing but r cubed. So you see this 1 by r to the power 6 and this 1 by V square are basically the same thing. To cut a long story short, what you learn in your thermodynamics textbook is nothing but a manifestation of this van der Waals interaction. Okay? So anyway, so this is the effect of surface tension, and so if you now place, let's say, a drop of liquid on a solid surface, most of you know that it takes a hemispherical shape. There is something called the equilibrium contact angle, and so that's basically based on the balance of the surface and interfacial forces at the point of contact. And now, something you can do at your home, put a drop of water, just spread it with your fingers. What will you see? What you will see is here, and in some places, this is on a table which is very rough, some places you see the contact line is retracting back. You see it's retracting back. So what actually is happening? What is happening is you have done something like this. By applying some energy from outside, you have spread it more than what can be balanced by its surface tension. And therefore, in order to sustain or restore the balance, it retracts back. This is a phenomenon of de-wetting that brings smile to Kajridi's face, of course, for obvious reason. This is very simple. And here, we talk about different reasons for triggering flow, like pressure-driven flow, quet flow, this, that. Here is an example of a flow which is triggered by surface tension imbalance. And contact line dynamics, Professor Dasgupta is the expert on this topic. It also triggers several very, very important questions. Does no-slip condition remain valid at this length scale? Because you actually see a contact line is retracting over a solid surface. Something more interesting is another parameter called contact angle hysteresis. It's just this, you take this drop, put it on a tilted surface, and you sometimes see that the drop is not moving. Have you all seen this? The answer is yes. After a splash of rain, many times on your horizontal, on your vertical window panes, you see a lot of water drops stuck, right? The question is, there is a net body force acting downwards, so why doesn't everything flow? It doesn't flow because of something, the interaction or the adhesion between the water molecules and the solid surface, which is, I won't go into the details of it, which is known as what is known as the effect of pinning. Right? This is one small story, and then I'll move on to another quick story. So, Professor Dasgupta wanted me to talk about this, so I think I will just briefly mention. So, instead of a flat surface, if you have structured surface, that leads to some additional complexity in the wetting state, and it can lead to, under certain conditions, super hydrophobic surfaces where water drops roll very easily, and things like that. These are quite well old concepts, 70-year-old Cassie and Wenzel states of wetting. But today is something I'm not going to talk in detail. So yeah, these are very important actually. The whole physics leads to what is known as the self-cleaning surfaces, because you have a hydrophobic surface, a drop of water rolls down it and picks up all the dust, right? So if you ever worry or wonder why these tall buildings with shiny glass facades, they are so shining, right? This is the secret. Most of them come with a coating of this type of self-cleaning surfaces. While the reality is that if you leave your car or cycle outside for 5 days in a country like India, it gets covered with a thick layer of dust. But these type of hydrophobic surfaces are not only they're important in these type of fancy applications, even in your classical condensation, for example, in your heat transfer textbook, if you have studied it, you would always like to extend or enhance the dropwise condensation regime to have higher heat transfer coefficient. And the secret to that is having hydrophobicity that will favor by quicker removal of water. Very interesting stories. So if you just leave a drop on a surface, let it evaporate, what do you think will happen? So this happens all the time. Some liquid has fallen on the table and it slowly evaporates. If you look carefully, you would expect that the liquid drop will become smaller and smaller before everything is gone with the wind. Well, it depends on the nature of the surface, and there can be different regimes. So you can have a continuous retraction of the contact line, or you can have something called intermittent retraction of the contact line. This is just a prelude to something more interesting. And instead of a pure liquid, if you now have a solution drop which is evaporating. Many times what happens, a drop of tea or coffee or dal maybe has fallen on your shirt, and after it has dried up, you get a stain. So what would you expect that if you have a drop of coffee fallen on your white shirt, you will get a stain spanning the entire footprint of the drop. Many times that does not happen. What you see is a very unique type of deposition pattern where most of the solute gets deposited radially along the periphery of the drop. This is what is known as, and this is what you see under an optical microscope. This is for a polymer drop. This is for a sodium chloride drop, so you see signs of sodium chloride crystals also. And this is actually an optical atomic force microscope image. So this thing is known as, very popular science, coffee ring effect. So because if you ever see a drop of coffee on a solid surface, you will see that you have a radial ring-like deposition. This was discovered in 1997, and it's one of the most well-explored areas of research. In fact, Professor Dasgupta's whole physics of contrasting blood stains with different type of blood rests on this whole physics, evaporative drying of droplets. I will just move on to, for the next 3 or 4 minutes, to something more interesting, or something equally interesting, I would say. So we just talked about this 1/6 dependence at the nanoscale, right? But what also needs to be understood that is basically a model, the Lennard-Jones potential, is if there is an interaction between two fundamental particles, like simple molecules or atoms. In reality, in most cases, you don't see the signature of this, but in nature, all the time what you see is two surfaces are coming in contact. I keep my cell phone on the table, two surfaces are coming in contact. After a talk, we clap, two surfaces are coming in contact. So a little bit of mathematics can be done from that model, and one can show that the scaling, so this is something comes in. Kajridi is the person to go to for understanding this very complicated equation. So what is shown is that between two surfaces, the dependence changes from 1/r⁶ to 1/d square. So what it means that this van der Waals interaction between two fundamental particles, which sort of stretches to about 10 nanometers, now stretches to something like about 100 nanometer between two surfaces. And when Professor Rajdeep Bandyopadhyay was mentioning, maybe up to 100 nanometer we consider to be nanoparticle, this is the exact reason for that, right? So that is also important, because you see, you get something like 2 micron, and you want to, let's say, impress any one of us by saying this is nano, so you write 2000 nanometer. Doesn't work. There is a reason why 10 nanometer there is some effect of confinement on nano, or even 100 nanometer there is some effect of nano, but at 500 nanometer there is almost no effect of nano. There is hard science based on that. So what does it mean? It means one of the, amongst other things, one of the topics about which this university should be very proud of, because one of your faculty members, favorite faculty members, have a lot of contribution in that, is thin films, or films which are thinner than 100 nanometer. So these type of films become special. Why? Because we now understand that between two surfaces there is some interaction if the thickness is, or if they are closer than 100 nanometer. What is a film? Film is essentially a thin layer of liquid bound between two interfaces. One is the film-air interface, and the other one is the film-substrate interface. So what happens in films which are thinner than 100 nanometer, I will cut this part of the story, I won't go to the story of Laplace pressure and all that. So there are always some fluctuations on the surface of a liquid film. These are basically because of the internal kinetic energy of the molecules. The biggest example of this is evaporation. There is evaporation at room temperature. That is a manifestation that kinetic energy of the molecules have a distribution, and some molecules have higher kinetic energy. So what happens is at the nanoscale, or for films which are thinner than 100 nanometer, these fluctuations may grow in time. So there is a video. So I'll tell you what is this video. This is actually a polymer thin film, which is about 40 nanometer thick, under an optical microscope. You do nothing. You just heat it up, and you see the film is disintegrating on its own with the formation of holes and something. Right? So this is a higher magnification image. And you can see that you don't have to do anything. Just based on the system thermodynamics, this film evolves into some isolated droplets. It does not remain stable, right? So this is a very, very important topic, not only for physical understanding or physics. Of course, it involves very rich physics, but it is also very important to microelectronic fabrication and areas like that. So Kajridi did a lot of theory on that, and I did some experiments on this whole area. I won't go into any of those details. So you typically use a polymer thin film in experiments because polymer, you can heat it up and take it to a liquid state by heating above its glass transition temperature. Therefore, it behaves like a liquid. And you can cool it down below room temperature. Just like that, this video you can pause at any point of time. With polymer, experimentalists can literally pause this evolution process, go for high resolution microscopy and very, very fancy stuff like that. Last question or topic that I'd like to talk about, whether this physics is good or bad. From the standpoint of physics, it is very good because it involves very, very rich physics. So we get a lot of publications, a lot of physical review letters, Nature materials, everything is there. But from the standpoint of a coating, this is extremely undesirable. Where does this type of films remain? Let's say many of us wear spectacles these days, and most of these spectacles come these days with some sort of smart coating or the other. If it is a child, you will go for an anti-scratch coating. If you are driving on the highway, you will go for an anti-reflection coating. If you frequently have to come out from an air-conditioned office, you go for the anti-smudge coating, right? Now you understand, if you want to make these coatings very thin, you will see all this fascinating signs not under your microscope, but on your spectacle, which is undesirable. So you make it thicker. And in the process, what happens is every material has some sort of optical absorption. So the thick layer starts absorbing light. So the lumen that reaches your eyes sort of starts to reduce, and unknowingly you start wearing a sunglass, which is not desirable. So there is a lot of science also that is going on in stabilizing these films. And one of the strategy for stabilizing such films is by addition of nanoparticles. These are very, very small nanoparticles, 1 or 2 nanometers, because the polymers we use typically have radius of gyration of 5 to 10 nanometers. This is an area which has been active for the last 20 years or so. So what is interesting, why I decided to bring up this story? So the story is that if you have these particles in the system, these particles eventually migrate to the surface. And if change the effective wettability, add stability, change the sign of the Hamaker constants, all sorts of things. But one fundamental question is, why does this particle even migrate to the surface? And simple basic thermodynamics comes into the play. Because if a particle goes and migrates to the surface, it releases a polymer chain, and that means the conformational entropy of the chain increases. So it's again very basic thermodynamics which we all learn in our undergraduate level that drives this type of phenomena. So I won't go into publicizing what type of work we did. Some snapshots of some of this recent work. We have been working on this nanoparticle mediated stabilization and morphology modulation. This work also took us to use, I'm primarily a microscopist, I use the atomic force microscope, but then we realized that once you have a stable film, microscopy is of no use. You have no idea where the particles are, right? So we started using the X-ray scattering in a very, very clever way and started going to the synchrotron. So Department of Science and Technology has a dedicated beamline in Japan. So we go there, and if you just look into this particular image, this actually tells you the density of the system as a function of its depth. So we had some nanoparticles, and we could figure out how these particles are migrating to the surface. More of a convincing proof of what people had been conjecturing. So that is sort of the concluding remarks. So we sort of understand, hopefully there is some take-home message of what is so special about nanoscience. The effect manifests in different ways, and one of my favorite examples is this spontaneous instability in ultra-thin film. And we also are working on stabilization of this, or overcoming the spontaneous instability by the addition of nanoparticles. And something I skipped is these nano patterns can lead to change in the wettability of the surfaces. So I must acknowledge the funding from CRB primarily and Solar Energy Initiative of DST. And I must thank this place. Some of you might be able to recognize this person, Professor Chiranjeev Bhattacharya. I could not find a good picture like Professor Dasgupta. So this is all what we could find. There's a picture of mine in 1993. I have put on a lot of weight, doubled my weight, and have become, in Bengali, have become mota, and I'm worried if matha has also become mota anyway. And this is a picture from 2023, with a batch of some 100 students in IIT Kharagpur. So that I have the strength to face a class of 120, 150 students is because of the learning I received here. Thank you very much. It was a pleasure talking to you.
Thank you, Professor Rohibrata Mukherjee, sir, for your interesting information in the field of nanoscience and nanotechnology. I would request the audience if there is any questions regarding his lecture. Any questions from the audience, please?
Whatever I'm studying is advanced chemical. How it is related to chemical engineering? Because all the phenomena, that's a very good question. All the phenomena that is happening is nothing but some of the unique processes that you have done. Whatever is shown, it's either fluid dynamics or it's diffusion, and most of the cases this evolution or whatever is happening is based on thermodynamics. So that empowers me as a chemical engineer to tackle some of the most apparently difficult physics problems. But when we look into the whole message of my talk was that most of the stuff is actually I'm contributing to physics.
Thank you, sir. Now I would request Professor Kajori Kaur ma'am to facilitate Professor Mukherjee.
She was my BTech supervisor and I made her completely mad.
উনি সুইচ ওভার করে দেবেন একদম পুরোটাই, ঠিক আছে? হ্যাঁ।
So, introducing our next speaker, Professor Dr. Manoshmita Bose. So, she received her bachelor's degree from Jadavpur University, Kolkata, and MSc and PhD from IISc Bangalore. She worked as a postdoctoral fellow in Monash University, Australia. After a short stint in industry, she joined Department of Energy Science and Engineering, IIT Bombay in 2009. Her broad research interest is granular and particulate flow. She is in particular interest in state-of-the-art experiments in multi-phase fluid flow, such as particle image and particle tracking, velocimetry, and discrete element method of simulations. She also worked on thermal energy storage technologies.
Good afternoon, everyone. It's my heartfelt thanks to the organizers, the head of the department, the professors, and my teachers. It's my privilege to be here. And when I decided to talk, I thought I would talk on a very focused topic on thermal energy storage system design and development that we have been working on for past 8 years. And then as usual, Kajori Di, who has been holding my hands for several decades now, suggested me to give a broad overview of our current research. So I just I added a couple of slides at the last moment, and I'll give a brief overview first under the same title. Okay. So now let me begin. you know, we work in broadly two different areas. If we divide the research of my group, our group, one is particulate flow and granular materials. Here we see that this is an example from pneumatic conveying system, an image from dune formation in the transition regime. I'll talk about it a little bit. And here we work on, last two speakers have spoken about nanoparticles. I bring you back again to the millimeter, submillimeter, and the micron range. So to them, they are giant particles. So here we work on simulation and experiments with these giant particles. For us, the small particles, few hundred microns, if not a couple of millimeters. Okay, so this is one area which we work on. And the other area is thermal energy storage, which I'll be talking in the second half. After a couple of minutes, I'll start talking about that part. Okay. Now, in this department, as all of us grew, we have learned about fluidization. I know I see some BTech students here. You have learned or you will be learning. So when we learn fluidization in textbook, we learn about minimum fluidization condition. That is true for monodisperse system. There is a minimum fluidization condition. We say that there is a balance between the drag force and the buoyant bed weight. What happens if there is a particle size distribution? Do we get monodisperse particles at the first place? Is it possible that we get a monodisperse particle as the first place? We don't. Do we get bidisperse particle as the first place? Suppose, imagine we get bidisperse particle as the first place, that we have in the size distribution curve, we have two peaks. If we get that, we get two characteristic points. And how do we get those two characteristic points? Fluidization, which is, as a technology, is a new technology, roughly about 80 years old, started and developed during the Second World War. The initial experiment started with pressure drop measurements. So from the pressure drop measurement, looking at the pressure fluctuations in the pressure drop versus gas velocity, superficial gas velocity curve, people found out the minimum fluidization condition. Now today, we can use simple camera, not the way the previous speaker spoke, like, my classmate, Robbie, that we use very sophisticated, so I bring you back from synchrotron to what? DSLR. So with a DSLR camera and a pressure transmitter, not just a manometer, a little sophisticated instrument, a pressure transmitter, simultaneous measurement, what we could figure out that between this initial fluidization condition and the final fluidization condition of a so-called bidisperse particles, there are several other states. What happens? Now, several other states, one has to remember here is, whatever visualization we are doing, we are looking at from the periphery. In a dense bed, we cannot optically see the bed because it is dense, it is optically opaque. So we are looking at the periphery, and unless and until we are completely convinced that whatever we are looking at from the periphery, we cannot say that this is a characteristic point or it is a characteristic of the bed. So one point we could identify that even when we do the simultaneous measurement of pressure and the bed physics, we see that between these two limits, there is another limit where the small particles in the what do I mean by bidisperse bed? That there are at least two distributions either in terms of size or in terms of density, or both. We are looking at the size distribution. So that means there is a small particle and there is a big particle. So what happens in the fluidized bed? In the cage formed by these big particles, there are small particles, and so there is at least a characteristic point when these small particles, which is caged between the big particles, they get fluidized within the cage, and then they start coming up from the cage, and then they travel up to the bed. That intermediate point does exist, and that we can identify using a very simple experiment. However, this we have to remember that this is a measurement from the periphery. We can the other interesting phenomena that we can see, that there is a crack formation, crack propagation that we are seeing only using this simple experiment. We can see only from the periphery. For a conclusive answer, we need to do tomographic experiment. There we need to, of course, definitely get into sophisticated experimental technique. Let me see if the video works. Now that you know that between this minimum fluidization and final fluidization, when I said there are other points, is it unique? Like, what do I mean by unique? When we have this, in the video there is no sound, but it should play. Yeah, okay. So now, when we have this dispersed media, we can have different initial condition. Initial condition could be homogeneously mixed, or it could be one top of the other, like completely segregated bed. If there is a complete segregation in the bed and it is inherently unstable, that means the lower particle at the bottom of the bed and the larger particle at the top of the bed, then what happens? There is a slug formation. Slug formation is known for fluidization. For which kind of particles? Cohesive particles. Here we see the slug formation in the non-cohesive particles. And why does this happen? Because the smaller particles get fluidized first. They bring the larger particle to the top. But as we keep on increasing the gas velocities, this is not a solid block which has gone up. So as we keep increasing the gas velocities, this is not a solid block, this is large particles, they get fluidized. And the large particles, then they are individual particles. They start falling. Now this movie is not complete. At certain point of velocity, the entire block actually falls off, and then the final fluidization state starts. So what do we know? That depending on the initial fluidization initial condition of the bed, we get different features of fluidization. Again, very simple experiment. Now moving on to slightly sophisticated experiment. Not that everything we can do with DSLR camera. Pneumatic conveying system, another very widely used system in industry. But this is a decade-old plot which is known as Zen's plot. Again, textbook material, we have seen it, pressure drop versus the fluid gas velocity. What we would expect if there were no particles in it, if it was a pure fluid, what we would expect? Pressure drop would increase as the gas velocity increases. Initially linearly, after that quadratic. What happens in pneumatic conveying system? Propels. But then there is a minimum point, and then pressure drop starts increasing. Dilute phase, transition, dense phase. And this transition phase, it's broken line because there is a pressure fluctuation seen. Why is it seen? Here, this small dune-like structures form. So everywhere in the conveying line, it's dilute phase. When I say dilute phase, again, in gas-solid suspension, there is no unique number for dilute or dense phase. Here, the bulk volume fraction for dilute phase is 10 to the power minus 3. And these dunes, which we are seeing here, the volume fraction is very high, 0.7. Okay. So dune to the bulk phase transition is very sharp. Now, do we get to see this if we use a DSLR camera? No. For that, we need slightly more sophisticated instrument. Using a high-speed camera, we can capture the dune velocities. And this is exactly how it looks in a pneumatic conveying line, in the dilute to dense phase transition. Why is it of interest to anyone, because the formation of these dunes, which goes to this kind of shapes, it forms, it diminishes, it gets washed out, again it forms, sometimes it forms a stable zone. If it is a stable zone, then there is no issue, stable pressure drop. But when it is forming and diminishing, it causes pressure fluctuation. Is there any connection between them? If we take the images of these dunes and do the image processing, either the position or the height of the dune, we measure them, and we have simultaneously we have measured the pressure signal, we analyze the data in the frequency domain, we see that the dominant peaks match, dominant peaks agree. So that means they are correlated. There is a correlation. But why is there, what is the relationship between the fluid flow and the dune formation? It's well known again from literature, the knowledge we derive from the literature, the presence of particle either augment or attenuate the fluid flow turbulence, depending on the volume fraction. Now, there is a possibility that closer to the wall, see, this is, in this case, the flow is happening in the left to right direction, and the gravity is in the flow normal direction. So there is a possibility that closer to the wall, since the volume fraction is higher, the turbulence is fluid phase turbulence is attenuated, and in the dilute phase, it is augmented. So this actually assists the deposition of the particles near the bottom part of the convening tube. Now, if we want to understand that, we have to move to one level more sophisticated instrument, because now we have to measure the fluid phase turbulence as well as the particle phase dynamics. For that, we have an excellent facility supported by the Central Facility Scheme of IIT Bombay. Under this scheme, we have high-speed PIV lab. PIV stands for particle image velocimetry. In that, what do? We have a laser here. It is a dual head laser. What does it mean? It means it sends two laser pulses, spanned between as small as 5 microseconds. So these two pulses, if it comes, we can capture the images of fluid flow between 2 microseconds, that means turbulent flow, multiphase turbulent flow, we can resolve. Okay? And with that, we can find out whether there is an interaction, or of course there is an interaction, but what kind of interaction that is there between the particle phase and the fluid phase, and what assists or what is causing the formation of dune. And this is a glimpse of the experiment that is going on at present in the lab. Now, parallelly, we are also working on the simulation part. This is one simulation I am showing where we are looking at the particle level interaction, single particle collision with the wall, because as I said, in the granular material is formally defined as a large collection of small particles. Now, the large collection, the behavior of this large collection is decided by the interaction of these small particles. So we try to understand the interaction of the small particle. Here is a cartoon of the wall particle interaction, and we have seen that when we are looking at this wall particle interaction, the correct implementation, it's not that we did a very profound work, but just looked at the correct implementation, and the correct implementation actually took the model very closer to the experiments performed. And then we are thanks to Robbie, I don't have to talk about van der Waal model and all. He has done that job wonderfully. So when we work with this, work with this model with contact forces, here the contact force, of course, when he talked about this repulsion phase, the contact force for us is a spring force. That spring can be a linear spring or it can be a non-linear spring, a Hudson spring. The contact force and the force and the cohesive force. The cohesive force is the van der Waal force. We work with large particle systems also. And we looked at how the particles, not nanoparticles, but micron level cohesive particles, how they agglomerate, and this we apply in fluidization and vibrofluidization. With this, I move to the work that I initially intended to talk on thermal energy storage system. A question can be asked, like, when we talk about solar energy, nobody thinks about solar thermal energy. People think about only solar PV. So what makes me talk about solar thermal energy and thermal energy storage? There are a couple of things. If we know that there is a 1 megawatt installation in Brahmakumari, and also if there are large kitchens, like when in the morning Juma and the others and Professor Sengupta, both of them talked about sustainability. They talked about the societal issue also. So the large kitchens actually they implement the solar thermal technology, and from that aspect and several other aspects, thermal energy storage is not only for solar thermal technology but also for process heat. And with keeping that in mind, we started looking at this looking at this thermal energy storage problem. So this is the unit where we are working on. That has a heating block. That can be solar, that can be any other means. By any other means, there is a heating block, and there is a demand block. Demand block can be the generation, if it is power plant, or can be anything else. The steam itself can be used. Thermal storage decouples generation from collection. That's the main purpose of it. It eliminates short-term variation, shifts generation to peak demand periods. And if it is solar thermal, then there are other benefits also. It avoids defocusing of mirrors during peak radiation, improves plant load factor. I'm not getting into all these details. Now I'll give a very brief overview, and this is basically for the students, that what are the types of storage? Now, what is a broad classification? We have sensible heat, latent PCM, and thermochemical. Okay? And then sensible heat, solid, liquid, and liquid solid. Solid is something nobody thought about. In literature, we don't get any article on solid thermal storage system because it has such a low specific heat. But practical, India's 1 megawatt thermal power plant in Brahmakumari has used solid storage system, not for specific heat. They use huge mass, so heat capacity increases. Okay, and then this is where the literature is very rich. Latent heat. This is a collection of literature, again mainly for the students, just to have an overview that the most common PCM is brine and used for fisheries, used in fisheries. There is a whole lot of PCM based material used for storage in buildings, and very little and research is going on for high temperature PCM. Why do I talk about this? Because I was very fascinated. Earlier I never used to talk about this thermochemical energy storage. But now I speak about this because the column that they use for as the reactor unit, that is a fluidized bed reactor. And fluidization is something which is very close to my heart. Now this is one of the reaction, hydration and dehydration of calcium oxide. There could be other reactions as well. This is yet another example. Now I move to this sensible heat base, which I intend to talk about. It could be liquid and liquid solid. Liquid solid is something, liquid solid sensible heat storage unit is nothing new to chemical engineers because it's like a packed bed. Basically, it's like a packed bed which is used by in the renewable literature as thermocline based storage unit, the storage system, the results presented in a different way. Liquid one, there is this 2-tank storage system which I'll be showing here. So there are 2 tanks, hot tank and the cold tank, used quite a lot commercially. However, now the focus is on the single tank storage system. Why is that so? Because cost, this is a completely applied problem, so there is a cost reduction of 33%. So a single tank storage system can be built in 2/3 cost of a 2-tank storage system. I would like you to focus on this column. These are the installations, and I have just compiled them. The numbers, look at the numbers, 19.9, 510, and so on and so forth. And the next one is 10, 1.4, 1.4. I mean, there is an order of magnitude reduction from 2-tank to single tank. Single tank storage system is in research and development stage, not too much in the commercial stage. The analysis is based on the energy efficiency, and exergy efficiency, energy delivered by energy ratio of energy delivered to energy stored. And when it comes to exergy, there is the quality of energy that comes into picture, that is the temperature at which energy is available, that comes into picture. Nevertheless, whatever it is, what is important is that in a 2-tank storage system, I'll go back to this slide, sorry for this. In a 2-tank storage system, there is a clear-cut difference between the hot temperature and the cold temperature. However, in a single tank storage system, there is a gradient. So the energy efficiency depends on this span of the gradient zone. And that gives that, that one has to, the research is basically now, the applied research is basically now how to reduce this gradient zone. What kind of design one can think of to reduce the gradient zone. I'll skip these slides because I have spoken that in the single tank storage system there can be 2 configurations people can think of or people are working on. One is the packed bed, which is something known to us. The other one is we don't have a packed bed, but we use different kind of flow distributor. Again, this is not something very new to us. This is there in literature for last few decades if we dig in the literature of chemical engineering. However, the results that we are presenting and the results, the way we are interpreting, that it can be used for thermal storage. That is the only difference. Now, we have started working on this particular flow configuration, that there is a vertical porous wall distributor and the hot fluid, it comes through during the available hour. Hot fluid comes to this porous distributor, and when it comes to this porous distributor, it replaces the cold fluid, and there is a thermocline zone that forms. There is a thermal stratification, hot fluid zone and the cold fluid zone, and in this gradient, this is the gradient zone, and we have observed, this is just an observation, we have observed that the gradient zone is very thin. In fact, we have achieved something about 20% of the tank height. What is so interesting about it? I'll skip some of the slides now. So when we started the work, keeping these questions in mind. Effectiveness of flow distributor, whether it is established in a tank, because when we started the work, that time there was not much work happening in the single fluid system. And then what happens if there is a temperature fluctuation in the charging cycle? This is called a charging cycle, when the hot fluid is introduced to the storage. And what is the effect of other parameters? Now, this is where we actually address the problem. We made a pilot scale system, which is 30 kilowatt hour system. Then we made a 4:1 lab scale system. So when Professor Goody showed the picture that lab scale to pilot scale to plant scale, I remember this, that we did a pilot scale to the lab scale. Of course, we didn't go to the plant scale. And then at the same time, we started working on the simulation. Okay? And this is how the molten salt looks like. We started working with molten salt. This is the solid salt, porous, flaky thing. We melted it, measured the viscosity. Viscosity had the expected behavior. That's okay. And we did the simulations, identified the parameters. Results, I'll skip most of the results. I'll show some of the results that we found out that the system is scalable. Good. With the flow, when we added the flow distributor, that is a porous distributor, stratification was improved, expected. What is fascinating about it? There is a porosity effect of parameters, fine. We introduced a thermal fluctuation. What do we mean by thermal fluctuation? That hot fluid was introduced, and during the as the hot fluid was coming in, we simulated some fluctuation, that is, we introduced a cold fluid. And then we wanted to see what happens at the system level. Okay, the porous distributor can absorb the thermal fluctuation, good. But in the simulation, what happens? And this is where, again, I would like to address the students that, a fairly straightforward, applied problem, very, very engineering problem, can lead to a very interesting phenomena. When we were doing the simulation, we started seeing these patterns. After introducing this thermal fluctuation, we saw this rolling up of fluid. Now, what kind of instability could it be? Says that doesn't seem to be a Rayleigh-Bénard instability, because the patterns are here, not here. It's not a Kelvin-Helmholtz instability. And then when we looked into the literature, so what did we do? We focused at one point and draw the time series. We focused at a line, single line. We draw again. We plotted the temperature and the velocity, and we saw the fluctuation. And when we looked into the literature, yes, there is a instability which is there, which is known as E instability. The instability is due to viscosity stratification. So through a pipe, this is again a pipe flow is linearly stable. What does it mean? That if a pipe flow is perturbed, somehow if we can externally perturb, but the solution will always be stable solution. However, if there is a viscosity stratification, what do we mean by stratification? That means one layer of fluid has one viscosity, say this be mu1, the other layer has another viscosity, mu2, the flow becomes unstable. Now what happens in this particular case, in our case? There's hot fluid everywhere, the outer layer has lower viscosity, then we have introduced the cold fluid which has a higher viscosity. Now there is a viscosity stratification here, and that viscosity stratification has led to the instability. So temperature-driven viscosity stratification leading to instability. And how did we again show that, that maybe we are correct? We have looked at the data in the frequency domain. So the take-home message here is that any problem which we start from a purely applied point of view can lead to an interesting fundamental problem as well. And with that, I would like to conclude my talk. With that message, I would like to conclude my talk, thanking my club collaborators, Professor Kedare, who has enthused me to work in thermal energy storage, Professor Bandyopadhyay, who has worked on, with whom I have worked on the system level integration. I didn't get time to talk about it. Professor Shankar, who has guided me through the instability problem. Dr. Varun Joshi was a postdoc, Dr. Praveen Gajviye was a PhD student, and all MTech students who worked with us. And then finally, I have to talk Professor Bhawal, Professor Abhijit Bhawal, Of course, all the teachers in this department who have taught us, particularly Professor Bhawal, who has inspired me to take a step forward and to go to IISc Bangalore, which has helped me shape as a researcher and do whatever little I am doing with my very limited capability. Thank you, sir. And finally, to all of you,
So sorry, due to time crunch, we aren't taking any questions. I would like to request Professor Dr. Abhijit Bhawal to felicitate ma'am. So next we will be starting the invited lecture session, and like the very first speaker we have Dr. Taposh Das. He is a fellow member of the American Institute of Engineers, past chair of the AICHE's Environmental Division, and former chair of Air Pollution Control Committee of the American Academy of Environmental Engineers. So can we start the session, sir? Sir, sorry, sir, we need to just wrap up the session.
Yeah, please. And I'll give you more PowerPoint. Oh. Oh,
idea of the natural convection, and Hartmann number will give us an idea of the electromagnetic force. So yeah, these are the boundary conditions. So for in the hot world, in the boundary condition for the hot world, then there theta will be 1, and the expression for the Nusselt number is also given here. So it is useful because from here we can study the heat transfer, and we can finally identify that which combination of this numbers can give us the most useful output. So in all our study we have taken the Rayleigh number in a range of 10 to the power 3 to 10 to the power 5, Reynolds number in a range between 10 to 200, and Hartmann number in a range between 0 to 70. And the volume of the cobalt nanoparticle is taken as 1%. And we have used contours of streamline flows and isotherm for visualization of the plot. Before doing this work, we did a validation study from where and here the results are shown, which shows that the results which we obtained are in accordance with the published results. We have just compared our result in our finite element solver and just checked that and whether it is in accordance or not, and in each and every case the error is less than 3%, so we continued with that. So in this case, we can see how with the effect of varying Reynolds number, when Rayleigh number and Hartmann number is fixed, the value of Rayleigh number is 10 to the power 3 and Hartmann number is 10 in this case. So we can see when the value of Reynolds number is 10, at that case only vortices are forming in the lower groove, but as the value of Reynolds number increases, the vortices are forming in the top and lower both the grooves. This is because here the forced convection is playing a dominant role as the value of Reynolds number increases. And in case of isotherm, we can see that when Reynolds number is 10, in that case the isotherm is of stratified nature, it is in layers. But when the value of Reynolds number increases, due to the vortices which are forming as the Reynolds number increases, for that reason there is a disturbance in the isotherm as well, and for that reason it is not in a layered manner and it is become more of a non-uniform pattern. So this is the effect of the Rayleigh number. We have taken Reynolds number and Hartmann number to be constant. We have taken Reynolds number to be 10 and Hartmann number 10 as well. And we can see that when the Rayleigh number is on the lower side, that is 10 to the power 3 or 10 to the power 4, there is a situation where natural convection is not dominating. We can see that natural convection is dominating only at a value of 10 to the power 5. But in lower Rayleigh number cases, at that time forced convection is playing a dominant role. As a result, we cannot see any such vortices. Similarly, in the isotherms, as I described in the previous slide, as the value of Rayleigh number increases and the vortices are forming, they are at the value of Ra 10 to the power 5. Only in that case, there is some change in the isotherm plot. And in the other case, it is of stratified nature. And it is the effect of the Hartmann number. So we can see that, and in this case, we have taken Reynolds number to be 100 and Rayleigh number to be 10 to the power 5. And we can see that when there is no magnetic field, when Hartmann number is 0, at that time vortices are forming. But as the Hartmann number increases and at a higher value of Hartmann number, that is when it is at 70, there is no vortices. The vortices are very weak. And so we can see that as the value of Hartmann number increases, then the formation of vortices decreases. This is because the fact that the presence of the Lorentz force, due to the presence of the Lorentz force, it creates a counteracting effect in it. And in case of isotherm, here we can see that when Hartmann number is 0, due to the formation of vortices, we can see that it is not in a stratified manner. But as the value of Hartmann number increases, the isotherm also becomes in layer. So this is a table where we see how the combination of Reynolds number, Rayleigh number and Hartmann number affect the average Nusselt number. So we can see that when Reynolds number is at a value of 200 and Rayleigh number 10 to the power 5 and there is no magnetic field, Hartmann number 0, we can see that the value of average Nusselt number comes out to be 14.81, which is maximum. So that means in this particular case, the heat transfer will be very good. So this is a useful result. And yeah, these are the conclusions that when the forced convection parameter are within the thermal boundary layer, and also it helps to create vortices in streamline. The average Nusselt number increases with the increasing value of Reynolds number, And as the Rayleigh number increases, the flow strength and heat transfer also increase. As it was evident from the previous slide, the efficiency of mixed convection heat flow decreases as the Hartmann number rises. Yeah, it was like from here also, when the Hartmann number is 0, at that time average Nusselt number comes to maximum. And these are the references which we have used. There are many more, but these are notably the ones which we have considered. And thank you for your.
Okay, I missed your initial part. I was thinking outside. Could you please just put the last slide?
Are you talking about this one?
Yeah, actually, thinking about it.
Okay. So there have been various studies where many scientists have taken various shapes, various cavities, and they have seen the effect of natural convection, mixed convection. But while doing a literature survey, we didn't find any paper which dealt with the phenomena when there is a butterfly-shaped cavity with certain thermal arrangements. What will be the various thermofluidic properties going on of the nanofluid? For that reason, we try to understand what will be the result for this particular case.
Now, can you tell me why scientists are so interested in studying cavity of different shape and size?
Yeah, because of its many industrial applications are there, like
just tell me what.
Yeah, because there are various chips which can be used for as cooling reactors in many microprocessors. Also, it can be used in like radiators as a for cooling reagents. For that.
What was the value?
Yeah. We are given the Prandtl number because it is given in the energy equation for that.
What is the value of Prandtl number? Because it is in your equation, so you had to use it, put some value in your simulation, right?
Yeah.
So what value did you put in?
Sir, when we were doing it in finite element solver, at that time, sir suggested us a particular value. At this moment,
You don't remember, but do you remember whether it was of what order it was? I mean, it was around 1 or much more than 1 or much less than 1.
That means what kind of fluid you are treating?
Yeah, it is a cobalt kerosene nanofluid. Cobalt kerosene.
So what is the volume fraction of cobalt?
1%.
And you said that natural convection and mixed convection. Are you aware of any dimensionless combination of dimensionless numbers which gives the importance of natural convection over mixed convection?
Yeah, I have heard some rational. There is a particular term at this moment I can remember.
From the terms that you have here.
Yeah.
Which numbers can just from looking at your equations can you tell me which numbers, which equation can give you the is there any dimensionless parameter or combination of dimensionless parameters which would give you the value? So which would give you the importance? Just looking at the equations.
As I said that the Reynolds number will give us an idea of the forced convection, and Rayleigh number will give us an idea of the natural convection, and the Hartmann number will give us an idea.
Higher Rayleigh number means stronger natural convection.
Right.
Higher Reynolds number means stronger forced convection. So in your case, but how do I know? I mean, if my Rayleigh number and Reynolds number both increases, then how do I know whether natural convection will dominate or forced convection?
Yeah, when my Rayleigh number and Reynolds number both are increasing.
Both are increasing.
Yeah, at that time there is a particular result. Here, in the case of 10 to the power 4, we can see that there is no what is other formula. So from here we can get an idea that at particular value, the combination of RE and HA, that it is forced convection is still dominating. But when the value becomes 10 to the power 5, then we can see the formation of body cells and it is moving towards
kindly also zero Hartman number so that you can comment on how important your whether magnetic field is at all playing any role.
Actually, we are doing it for future work, but
any other question? There is no other question because while cobalt
yeah, because there are many fluids which can be used for thermal efficiency. We know that there are certain nanofluids which will affect the thermal efficiency and will certainly improve the heat transfer. We could have used other nanofluids like Al2O3, but we are going with cobalt kerosene because generally all the studies which we have encountered, mostly all the scientists have used as Al2O3 as their nanofluid. But here we wanted to see whether cobalt kerosene will make any such difference or not. For that reason we went with that.
Suppose we use Al2O3 instead of cobalt. Do you think all these parameters will still be important? Al2O3 or maybe simply aluminum nanopowder or copper nanoparticles. Do you think all these parameters will still be important?
I do think so because depending upon the fraction of the nanoparticle concentration which is there.
Hartman number will be important for which kind of surface?
For when there is a magnetic field, right? So
Hartman number is a measured magnetic field. So will magnetic field influence all any kind of nanoparticle?
Not all the nanoparticles. There has to be magnetic qualities which will affect the flow. Right. For there are some certain nanofluids which shows that kind of behavior. For that reason, we use that one. Like when we were going through the literature survey, we found that there are certain nanofluids which were being used.
दूसरा दिन आया था ना स्टिल वीडियो उनको अलग अलग वो पहला पिकअप था उनका 16 था 17 तारीख 17
Thank you, and that was the end of the technical session. Thank you, Professor Mukhopadhyay, for conducting this session. Next, we have an invited lecture session featuring lectures from Dr. Tapas Das of St. Martin's University, USA, and Dr. Shurali Bandyopadhyay from Department of Chemical Engineering, Norwegian University of Science and Technology, Norway. I would hand over the mic to Dr. Das to start the conducting of the next session.
কাছে কোন দিকে থাকে দেখে দেখে বলবো আছে যাই না কটা বাজে 8টা 8:30 পর্যন্ত তখন চলবে ওখানে আছে আবার ওদিকে এখানে কথাই শেষ হওয়ার কথা ওখানে আবার আছে ওইখানে
হলেই হয়ে যাবে।
অসুবিধা নেই 10 মিনিট পড়া হয় 10 মিনিট পড়া তো কোনো প্রবলেম নেই কেন বলো তো হ্যাঁ চলবে হ্যাঁ
ফেলিসিটেশনটা হলে তো চাপ
তো হয়ে গেছে আগে তুমি তুলেছো তো
হ্যাঁ কিন্তু
তো হয়ে গেছে খালি একটা লোকেরই বাকি ছিল ওই যে আমার খেতে গেছিলাম যখন তখন একটা লোকের বাকি যারা পারপুরি সব হয়েছে
ওই একটা লোকেরটা আছে আমার কাছে ছবি আমি মোবাইল থেকে তুলেছি এসে ক্যামেরা বার করার সময় পাইনি
ওই খালি আমার একটাই বাকি ছিল আমার পারপুরি সব ঠিক আছে ঠিক আছে খালি বক্তৃতা হবে
Let me introduce our next invited session lecturer. Dr. Taposh Kumar Das is a fellow member of the American Institute of Engineers, past chair of the AICHE's Environmental Division and a former chair of the Air Pollution Control Committee of the American Academy of Environmental Engineers. Dr. Das also serves as an adjunct faculty member at several colleges and universities in Washington. Everyone present here is well acquainted with Sir, so I would hand over the mic to him.
Yes. Thank you for your nice introduction. I feel like a homecoming. I want to really, it's a great privilege, I should say, or I'm very proud and fortunate to be part of this glorious 100-year chemical engineering centenary celebration. And thank you for being with my session. We had some technical issue, but it has been resolved. Hopefully it will move forward nicely from this point. As she mentioned, because the theme of this conference, 100-year chemical engineering, so I came up with this title of my talk, is 100 years of chemical engineering major innovations advancing towards sustainable development. And I will define sustainability and sustainable development later on. Most of you, all of you are familiar with those terms. So I'm at a Catholic universities over 130 years. We have a School of Engineering, Civil Mechanical, and I've started environmental engineering now, and I'm part of that program. And then in the state of Washington, not far from Seattle, big city. There was a paper published in 1988, Chemical Engineering Progress, which is a published paper for the Environmental Division of American Chemical Society. So that's the cover page of that paper. So I'm going to introduce what is chemical engineering. Actually, most of you know, but let's put some of the words into so we will understand the broader meaning. Chemical engineering is a dynamic discipline and multidisciplinary in nature, and it has been evolving continuously since the day of major innovations during prehistoric times, and played an important role in the development of chemical industry. It plays a key role in providing the most essential human needs, such as food, clothing, medicine, shelter, and so on, etc., to the mankind. Since last 100 years or so, we have been witnessing a change, emphasis from commodity chemical to specialties, synthetic to formulations, process concerns to product emphasis, homogeneous materials to composites, cost competitiveness to quality control engineering, and so on. The raw materials for both renewable and non-renewable to usable product, such as petrochemicals, specialty chemicals, fertilizers, papers, polymers, and plastics on a large scale, to colloids, to nanoscience and nanomaterials, as Professor Rajiv Banerjee alluded just before few lectures on the other lecture hall. harmful chemicals. So I will continue on that. Biotechnology and biopharmaceutical. Some of the speaker actually talked about biopharmaceutical, biotechnology, which is growing in India. Medicine, human genome, DNA sequencing, to the recent COVID-19 vaccine developed, and the list goes on. And because I added COVID-19, because chemical engineers actually played a role in the development at Pfizer, and I'll show the picture. The person, chemical engineer, was involved is a Bengali person. His name is Dr. Arindam Basu. Harmful chemicals such as DDT, insecticides were prevented, and industry safety and environmental protection highly emphasized after the large 1984, the tragic Bhopal disaster you still remember. So outline of this talk, I will take a little more time to say all words, so that will help us to move forward faster. Water resources, watershed, water and water everywhere, groundwater, surface water, storm water, grey water, snow-capped mountains, salt water. So water has all different forms, but they are water, and we have to actually nurture them. So then the watershed comes in, the wastewater treatment, primary, secondary, and tertiary are advanced industrial and publicly owned treatment works. Water reclamation technologies and beneficial reuse, recycling. Demand for potable water is rapidly rising across the globe, particularly in India, over 1.3 million people. So the water is our new oil or gold, and that is the question. So energy water nexus, we need water to make energy, we need energy to make water. Food, energy, water, they're all related. In order to make food, we need both energy and water, and so on. Defining sustainability and sustainable development, there is a slide later on. We'll define that and we'll see the wordings. And the sustainable chemical process and product design using green chemistry and green engineering principles. And then I'll conclude my presentations. So here we see this slide. As we see here, there's a river here, there's a power plant. For cooling tower water is actually provides from the river. So the power plant using the water, and they treat it as needed to meet the water quality standard, and then putting back into the water. So it is a closed loop system. The criteria is to maintain that water quality. Otherwise, cannot be reused once again. So that is the key part, and I'll emphasize on that point. So the next slide, as you see here in the state of Wisconsin River, I spent 3 years at the university there some years ago. There, the pulp mill by the Wisconsin River, they are using the water from the river, and lots of water, as you know, pulp mill use. So they were using the water and treating as needed, and then putting back into the river. So you see it's a closed loop system. And if you look at the after treated water, reclaimed water, it is as clean as our bottled water. And you actually can drink it in terms of the quality and the biological portion of it. It meets all the requirements. But by law, Department of Health in the US, you cannot actually drink it, because the drinking water has to come to the underground. But in terms of the quality is the same. Okay, let's move on. The green chemistry, the 12 principles of green chemistry. Of course, the first one, to prevent waste. Every atom has to be used, so your efficiency is going up, your productivity is going up. At least in theoretically, it has to be close to almost everything. Use the least hazardous chemical synthesis, design safer chemicals, and use safer solvent, no more ethylene, blue ethylene chloride, things like that, or acetone, auxiliaries, designed for energy efficiency, designed for water optimization, and integration, use renewable feedstocks, reduce or avoid the use of derivatives, use catalytic reagents designed for degradation, and choose inherently safe chemistry for accidental prevention. I'll just take one example to highlight the benefits of green chemistry. Before this principle, we used to use elemental chlorine to bleach paper, to wash hands, to a lot of things that chlorine was used, but then we found out that when we use elemental chlorine, we make dioxins and furans. Okay, that's the chemical symbol of the dioxins. Sorry. So, in order to avoid that, EPA, US EPA said we cannot use elemental chlorine anymore. So, what's the alternative? Of course, ozone and chlorine dioxide, those are all chemicals that do hydrogen peroxide, also strong oxidizing agent, and do similar things as chlorine, and they don't make dioxin. So we actually switch. Some people, they're using little bit of ozone, little bit of chlorine dioxide, hydrogen peroxide combinations of so that. So if you look at this next chart, dioxins were making at this level, pp parts per quadrillion. Okay, so but then once we switch to alternative chlorination, the dioxin is almost, you cannot even detect. Quadrillion level, 10 to the minus 12, and today's analytical instrument can actually see molecular level things, just unbelievable. So that's one example. So I'll switch on quickly. 12 principles of green engineering was actually made by Iceis and Zimmerman. First principle, designer need to strive to ensure that all materials and energy inputs and outputs are inherently non-hazardous as possible. It is better to prevent waste than to treat or to clean waste after it is formed. It will cost you more, and so on. And separation and purification operations should be designed by minimizing energy consumption and materials use. As you know, chemical engineers, the downstream are the problem. Separation is one of the major problems. Product process and systems should be output rather than input pulled through the use of materials and energy. Embedded entropy and complexity must be viewed as an investment when making design choice on recycled use or beneficial disposition. Targeted durability nor immortality should be design goal. Design for necessary capacity or capability. One size fits all solution should be considered a design flaw. Material diversity and multi-component product should be minimized to promote assembly and the value retention. Design of product, process, and system must be included in integration and interconnectivity with available energy and materials flow. Have two more principles: product, process, and system should be designed for performance in a commercial afterlife. Material and energy input should be renewable rather than depleting or non-renewable source. Okay? Thank you for your patience. As you see, 2 cycles. Well, let's talk about this manufacturing plant. Zero waste manufacturing. 2005, I published a book. The title was Towards Zero Discharge: Innovative Methodology and Technology for Process Pollution Prevention. From pollution prevention to process pollution prevention, made it to 3. So the idea, of course, theoretically, this is possible in reality, but we'll talk about it. Manufacturing plants will always see the materials coming in and the energy coming in, materials including water too, and all this you see is a clean product coming out. There is no stacks or anything or sideline. Anything byproduct that is either in the process going back to the front or going to the alternative process within that industry, possible. Okay, so that is the concept of manufacturing, zero manufacturing. And I have some case studies for that to actually emphasize this idea is not theoretical, you can actually do it. All right, so the upside model triangle, as you see here, typically you will make some product, your side stream, you massage them, you treat some way, and then you put it back into river, the water, or if it's a landfill, you solid waste, that's good. So all those waste actually nothing being reused or in that event, it is just the waste goes away from that plant. But the bottom line, as you see the waste coming from that top A is part of the operation. B and C, they are actually being reused, recycled. If you design the process carefully, you can do it. If some of the byproduct you cannot use it, maybe your neighboring industry, if you are in a cluster, in industrial ecosystem, then you could do that. It's just like our Mother Nature. Mother Nature doesn't really waste anything. It is always within the nature. Of course, we are talking about plastics, and Mother Nature sometimes don't like plastics to deal with. Okay, I'll come back to the plastics. So now let's go back to the bigger picture for which I'm here giving this presentation, sustainability, industrial ecology. Industrial ecology, just like the ecosystem, we are talking about industries that are acting like ecosystems, one taking their waste and making as a raw material, so it is remain within this industrial system. There is nothing going out of those cluster of industry. The concept of zero discharge or zero emission is the key to sustainable development, but is by itself or a subset of industrial ecology. Okay. Sustainability can be defined as follows. Sustainable development is the challenge of meeting human needs for natural resources, industrial product, energy, food, transportation, shelter, effective waste management, while conserving and protecting environmental quality and the natural resources that's essential for future development. It's all larger way explaining everything. I think that's all makes sense, but the World Commission on Environmental and Development, definition came around 1987. You probably heard this definition. I'll repeat again. The development that meets the need of the present without compromising the ability of future generation to meet their own needs. Okay? So go to the next slide. And here you see the three-legged sustainable systems. One of this economy, social, and the environment. Okay? So you have to gain in all areas. You just cannot gain economic area and then losing some of the economic areas. So you have to increase this middle part of it. All system expand as much as you can, and then you become more and more sustainable development systems. So we'll talk about it more in that term, but this is what we'll be envisioning when we talk about sustainability. So here is another, this is a 2020 book that I published, which is a textbook. I'll come back to that later. There are some of the few definitions I define: no defect and zero defect. What do you mean by that? If someone tells you just make this unit, exactly this is that, that's what you can do, exactly what it is, and the materials and so on. Minimum energy, renewable sources, more preferable way, if you could do that, that is. So there is no defect and zero effect. Effect means here on the human health or on the environmental side. Okay? This is not theoretical, this has to be applied. Process pollution prevention or P3, which I mentioned earlier. In the 2020, I replaced process with the profit. So it's going to be profitable pollution prevention. Means that you, with the one stone, you're killing waters, you handling pollution prevention according to the environmental laws and regulation. At the same time, you're making money because at the end of the pollution prevention process, that become a product that can be used. Could be water, waste treatment. Water is a perfect example because that water you're going to use more and more time. So the profitable pollution prevention, that is the mantra of our future activities in terms of solid waste, air waste, as well as water. Waste management in general. Okay, here we will focus on the best management practices, best available industrial manufacturing processes, techniques, technologies that treat raw materials into no defect product, as well as the innovative and emerging processes that have best potential for achieving the highest standard in pollution prevention at the plant and industry level, leading to no defect and zero effect. A common goal towards the industrial environmental management. Industrial environmental management is a very, very important areas which is going to develop in future. You see in a big way. That is my hope. And to move forward, NZ, the no defect, zero effect, via process pollution, profitable or process pollution prevention, industries must use processes that deploy material and energy efficiently enough to neutralize and control contaminants in the waste streams. The ultimate goal is to remove pollutants from the waste streams and convert them into product or feed to other processes. Okay? Like, as I mentioned, our mother nature ecosystem. Logically then, P3 refers to industrial manufacturing processes by which materials and energy are sufficiently utilized to achieve the end products that have no defect, while reducing or eliminating the creation of pollution or waste in the source that is zero discharge or zero effect, which I mentioned earlier. The primary goal is to educate the engineering students to prepare them as current and future generation engineers who will learn and practice sustainable engineering and who will be our champions steward in environmental, industrial environmental management as needed as a caretaker of this planet. Okay, why zero discharge is critical to environmental sustainability? I think I kind of alluded earlier, but I'll repeat again. To understand why zero discharge is critical component to sustainability, it is important to recognize that one principle of sustainability is the efficient and wise use of resources, and especially with regard to limiting the amount and type of resources, extraction, and subsequent pollution loading. To see how these are related, it may help to think a cycle with the three sources, systems, and sink. You have a source, you have a systems, and the sinks where your pollution is going either air, water, or in land. The systems is our ability to manipulate energy to turn source material into finished product. Economic and industrial systems are limited only by imagination when the first thing actually happens. The sinks are the global waste bin. The ultimate long-term sink is the deep trenches of the oceans. As you see, some of the plastic, microplastics. Short-term sinks are biosystems, such as the atmosphere. We put nitrogen, sulfur, mercury, and all that. Rivers, wetland, and land. The ability of the sink to handle waste is limited. Most to show adverse effect as pollution loading in just a few years. Okay. Going back to now water nexus, this is a little more practical terms and sustainable development. So just start with water energy, which is wonderful subject. We use every moment of that. So the water we need to make energy, and then energy to make water. Here is a very interesting graph. I got it from online. See, here is a river, and you see the houses, and you see a power plant in the middle. Power plant and the cooling water they're taking from the rivers, you treat accordingly, and then make sure the material don't get rusted and those kind of situation, or become soil the hardness because hard water. All those just to maintain the level of water needed, put it back into the river, because you know that water you're going to use it again. So you have to purify to the point you can reuse it. Okay? So that is actually the interrelationship between the water energy, just showing at that water boundaries where the water and energy are being used, and some of the residential people also benefiting out of it. Okay, I'm not going to repeat all that. I actually mentioned they're both interrelated, intertwined. Water is used in all phases of energy production in electricity generation. Energy is required to extract, convey, and deliver water to diverse human uses, and then again to treat wastewater prior to return to the environment. Energy water system could be developed, managed, and regulated cooperatively, not independently. Earlier I mentioned the cluster of industry, they are using river from the same, water from the same river, and then they're putting their treated water into the river. What I've seen in Wisconsin, when those plants use the water, they actually pump it to a central treatment system rather than having their own treatment system. That's become economical. Only thing that cost will be a little more to pump further, but they are not too far. Overall, the economy is actually good, and I have some economic data to illustrate that. That's a unique system if we implement it. But they've been doing that for many years. Now I'm going to bring the food and energy and water next. So the nexus between water, energy, and food and its interdependencies has gained increasing attention globally in research, business policy, and national security. The food security, the food, energy, water nexus is being promoted as a consumption tool for achieving sustainable development. So next slide actually showing we have a lot of sugar cane with the largest sugarcane producer after Brazil. And so from sugarcane you extract the juice, you make molasses, from molasses to alcohol. Now as you know, Brazil, most of the cars are run by alcohol. And then you have molasses, and so you have see the food from the crop, you get the food and energy together. The water that you need to irrigate is coming from the wastewater treatment plants. So you're growing the plant, and the water that we actually treated and you've been using. So water reuse, recycling also the integral part of this, the food, water, energy nexus. Okay. And near my house there is a treatment for the three cities: Lacey, Olympia, Tumwater, Thurston County. They have over 60,000, almost 750,000 people. They put it in all their wastewater into one place. And I took my students about 3 weeks ago to see that plant. It's state-of-the-art plant. And this reclaimed water plant, I'll go back to the reverse osmosis and systems they use. So they use some of this technology here, this listed here, in the membrane bioreactor. Their water is as good as you can drink it, and it is just excellent system that has this reclaimed water plant. I took that picture when I was there maybe 7 months ago, maybe last year. So it's a really excellent plant. I took our students also to see the plant. Let's see what I'm actually doing. This Lacey Olympia Tumwater, Thurston County reclaimed water plant. Is basically when wastewater coming in, you have this sedimentation to remove some of the solids, and then the effluent goes into aeration tanks. You have a highly mixed liquor suspended solids. You have a food and bodies ratio. Winter time you have a higher number, so you have more bugs to work around because they are a little bit slow. In summer you could come back a little bit lower, and so that way you estimate amount of sludge that will be generated. Okay, and that makes, you have a membrane right in the middle. When most of the bacteria broke down the carbonaceous BOD, biological oxygen demand, you're not going to nitrification. Denitrification at that point is already taking place. Is enough to have little nitrogen into water, but most of the carbonaceous BOD has been broken down. At that point, you have membrane that are taking the clean water and the remaining stuff right in the suspended solid. It is more energy intensive because, as you know, the pores are small. You have to really use a huge pump. So that is the major operation, but that at the benefit you get the high quality water, which can be reused for many beneficial uses. Okay, here it looks like those membrane module, they put it inside those activated sludge. It's got bundle of just like a spaghetti with a very fine pores in it. Okay, let's move on. And so what is reclaimed water? Sorry. Huh? Oh, I see. Okay. So reclaimed water, basically what I said, the water quality is reclaimed. You can actually reuse again. And there is a Class A, Class B, Class C reclaimed water. Class A is most preferable. And the cost, as you see, after 1,000 gallons, you actually make money, like almost $5 after treating. So you can imagine at the end of the year, you could use $7 to $8 million. That plant itself makes that amount of money. And here is the classification of water, Washington and California. Class A, B. A is the highest. B, C is a little bit lower, but that can be used in agriculture and other. But the Class A water, except drinking, you can use for anything else. All right, so let's switch. Class A to achieve, we have to use filtration. We have to use some coagulants in order to filter suspended solid. Then you can also use for cooling water and other beneficial uses. Okay, I think I've shown that some of the food crop irrigation, golf course irrigation, the class B and C can be used to grow some of the plants that as a fod that we could feed the cattle, not for human consumption. You can also polish your effluent in the wetland if you have land. And then, of course, this is the Mount Rainier. It's a beautiful site. I could see from our house from the Mount Rainier. So here is the golf course they use. So all those wastewater we saw at the lot have been used to irrigate these lands, and excess water they put it into the creek. So that water will be available somewhere else. And most importantly, they inject directly into the ground. So they know that water is in the ground, they can pump it and they can use it as a drinking water by adding some chlorine and other disinfection. So this is their infiltration basin, a huge area. I've been there, it's a beautiful site, and this is, see how green it is because of that. In summer, children go and play with the water. And now the picture I wanted to show, this gentleman, sorry, Dr. Arindam Ghosh, right in the middle. This was at the foundation dinner last year at the ICT meeting. This gentleman was actively involved developing COVID-19 vaccine. If you Google him, Arindam Basu, he has many patents and many, just incredible person. He's a chemical engineer for IIT Kanpur. Then he got his PhD from Purdue University. And Dr. Darlene Schuster, she is the elected president. I think her term expired, so we have a new president. And he's a Sankar Sundarshan, good friend. He's a professor in chemical engineering at Princeton University. I think I'm almost close to conclusion. Let me conclude with the chemical engineers displayed a significant role in serving humankind during the last century and will continue working into the future to meet our needs. So we shall celebrate as we came here our 100 years together. I think that's, I want to conclude with most water reclaim and water beneficial use has become commonplace in many countries due to increasing population, demographic shifts in where people live and industry locates, and current and future climate changes and water scarcity to meet societal demands, technological advancement, increased public acceptance, and improved understanding of health risk. Most reclaimed water body is used industrial agriculture and by delayed groundwater recharge. I showed you that, setting that meet the high quality standard determined by each state and the country. So the high quality standard is the key thing. So we invest money up front so we get the benefit. So I've been telling for last 10 years, I don't know if people are listening, we actually waste some money halfway through, we do not go and finish the job. So as a future engineers, a chemical engineer, civil engineer, pay attention. The little bit money, if you design carefully, you can actually get the reclaimed water high quality. So once you achieve that, then it will be a wonderful thing to happen and will be pretty close to sustainable development. And this is the picture of my first book, Towards Zero Discharge. Innovative methodology and technology for process pollution prevention. It is a 13-chapter book. I think chemical engineering department has a copy. I gave 2 copies. One, the simple one, gave the vice chancellor, and one was, I think, Dr. Shamul Shana, our teacher. Unfortunately, he passed away, and he was there when I actually gave that book in the library. And very recently, this is 2020 book. It is a textbook. I taught this course in Wisconsin. Then I realized there is no textbook in that particular area. It was a 485. All seniors took the class. I taught it very differently, passionately, and then I learned actually what are the importance of the subject matter that should go into that subject. And then I spent almost 1.5 years, 2 years. I made all table of contents, and then book came out. 2016, I committed to work on the book. In 2020, it's almost 4 years. It took for 3.5 years almost. And some of the references that I put in materials, 100 years there's a book. Was published from Louis Norton. He was the first professor at MIT. 1888 has a 4-year chemical engineering course. Can you believe that? Chemical engineering development in India. Ramesh Mashelkar, who was here, actually this morning I saw him and talked to him. He wrote a chapter, 100 Years of Chemical Engineering from Louis M. Norton, present, edited by Nicholas. His work was on India, chemical engineering in India, Professor Mashelkar. Then Professor John Ball, I have known, he's my mentor for over 30 years in University of Washington, Seattle. I saw him and he read my abstract. He said, "Tapper looks great, that should be fine." So he gave some advice, and then Professor Bruce Finlayson, he was a past chair of the ICT president, also professor at the chemical. Bruce also gave some advice. And those other books that I listed here, particularly ecological engineering, life cycle assessment, those things, and then the 12 principles, both in green chemistry and green engineering. So with that, I have to acknowledge these people who provided some of the beautiful pictures from the lot, Clean Water Alliance, and the Air Quality Program Department of Ecology, and then the Water Quality in Washington, D.C., and there's a consulting firm I worked for a while, Skillings, right there. And so I acknowledge them. And then the city of here, that the wetland and water treatment plant, they are the first treatment, public treatment plant. They demonstrated that reclaimed water plant. Their water drop that goes into river or anywhere else. All stays in the plant. And then the some of my students also in the civil engineering course. I really want to thank you for your support being with me this late afternoon. I think you were running late, but at least I was able to present, for which I came from all the way from. Thank you for your attention. Now I'll try to entertain one or two questions.
No effect and zero defect, as the title of one of the slides of Dr. Das's mentions. There was absolutely no defect, but the presentation and the lecture was absolutely very effective for us. I would request the audience if there is any question.
Look at you.
Absolutely. Thank you very much for being with me. I was a doctor. Try to entertain. And all the water is actually happening. Everything I said is in the US, but we're not too far away. It's not really a rocket science. No. I think it's just the science we do as we have to just we have to put our effort. Say we do that with us. We are halfway through. Yeah,
Our next speaker for the invited lecture session, Dr. Sulalit Bangwadhai, currently employed as an associate professor at Department of Chemical Engineering, NTNU, and a researcher at the Department of Water Management, TU Delft, Netherlands. His research interests include synthesis, characterization, and functionalization of nanoparticles, drug delivery, diagnostics, biosensing, modeling of nanosystems, development of nanoparticles, based hydrological tracers, and recycling of lithium-ion batteries. This is a brief introduction of him. Now I'm going to hand over the mic to him.
Thank you, and thank you very much for bearing back so late. And I'm also reminded of the days when we used to do hybrid teaching, so I will consider that there are, what I'm going to talk about today is going to inspire some of you, at least in the audience. So without further introduction about myself, because I think we will go through what work we are doing, I would like to proceed with what I've decided to talk today about, which is primarily on how we use chemical engineering to control the formation of nanoparticles and then how do we tailor those nanoparticles for applications within biodiagnostics. So I'm going to focus on a few examples, including one very highlight example for the last few years regarding the development of the corona test from NTNU. So the way I have decided to talk today is, first I'm going to give a very brief overview of how we do the synthesis, fundamentals of synthesis of nanomaterials, and then I'll take three different small stories. First, I'll talk a bit about gold nanoparticles, how we control their shapes, and how we can use those for biosensing. And this is going to fall back a bit on what Professor Rajdeep Bandyopadhyay talked about in the other hall. And then I will talk about silica-coated iron oxide nanoparticles and introduce what we have been contributing to the corona test from NTNU. And then we'll talk about polymer-coated iron oxide nanoparticles and how we use them, for example, in DNA size selection as an application. And then end with some outlook. So to get started, the very important fundamental for synthesizing any kind of nanomaterial, for that matter, or colloidal particles, is this driving force, which is the supersaturation. And that's defined effectively as a ratio between the concentration or activity of ions to the activity of ions at equilibrium. So you need a certain concentration above which you can start to precipitate those ions from solution into the first tiny particles. And this step is ideally called then the nucleation, when you have given birth to the first solid phase from a single phase system to a biphase system. And then these tiny nuclei, they start to grow. And that process is primarily referred to as a crystal growth. And then there are more size sharpening mechanisms and secondary growth mechanisms that follow. So keeping it very short, if you were to control sizes of these particles, you would like to control nucleation and growth. And that's exactly what we do in my research team, understanding and controlling these two processes at a fundamental level to tailor nanomaterials. So to have it even more simpler, if you start with these metal precursors that you want to assemble into the solid nanoparticles, if you do a very fast nucleation process followed by a growth, you would mostly end up with more monodispersed particles, and we have heard a lot about monodispersed particles in the other session. Whereas if you do a slow nucleation, more or less, and have a quite considerable control on the growth, you would end up with larger particles. In many cases, they would be also polydispersed. So with that background in mind, I would like to move on to the first example that I wanted to present, which is where how we synthesize anisotropic gold nanoparticles. So I think we heard about how we can use, for example, the surface chemistry of gold to tailor-make for detection of specific analytes. But we are concerned, or we are more interested in having shape anisotropy. So how can we control, make these small seeds grow into large rods, for example. So for that purpose, we start with a mixture of surfactants. The CTAB is a single-chain cationic surfactant. And then we add silver nitrate, which is more or less a growth directing agent, so it helps in shape control. And then we add our metallic precursor. So when we add that, it becomes yellow in color, so that's our growth solution. And then we add the reducing agent. And this is where the first step before nucleation can happen. In this case, what is important is there is no nucleation. We are only controlling growth. So this is seeded growth process. So once the gold is reduced from +3 to +1, the solution discharges, but it's not enough supersaturation to cause homogeneous nucleation. So we need to add in tiny seeds, and these are 2 to 3 nanometer CTAB coated gold seeds, on which now the reduced AU+1 will be further reduced to AU0 and start to grow. So in a few minutes, the solution starts to have a color, and if we leave it overnight, then you get basically whatever shape you want. And this has been the focus of our research for several years now. And what we have shown is that if we start from the spherical seeds by employing a mixture of surfactants, so this is a single chain surfactant, as I said, CTAB, combined with a double chain surfactant, which is DDAB, we can primarily go through a host of shapes. So we can tune the shape from bipyramids to tetrahexahedra to these beautiful rods. We can also cause some etching happening on the rods. We can also have these dog bone shaped structures or even bigger tetrahexahedra. And some of these are in the real nanoscale, less than 100 nanometer, where some of these are in the industrial nanoscale, which are more 500 nanometer, let's say. But what we wanted to emphasize in this field is that you can basically tune these parameters and get different shapes. So we wanted to actually visualize it based on the knowledge that we have within surfactants and polymers. Not everything is visible, I see from the projections. But we tried to plot a ternary diagram. And for those of you familiar with ternary diagrams, here on the 3 axes we can plot primarily 3 variables, and we can then start to look at which regions give rise to what kind of shapes. So, and then we had, remember we have also scaled the pH here. So these is normalized pH, that's why we can plot it from a scale of 0 to 1. But we can then go along these different lines, which are similar to tie lines or composition lines, and can go from one shape to the other. So the main thing that we tried to show here is that if you travel across these specific lines, we can transition from spherical particles to rods to bipyramids. And that is what this slide and this animation primarily shows. So after having worked on this, we wanted to really understand how this is happening, or what is the growth mechanism. So as I mentioned that if you are starting from 3+, there is a reduction step, so there's a reaction happening leading to AU+1, and then this AU+1 is transported to the seeds, and on the seeds it starts to then get reduced, and this is an autocatalytic reduction process. And finally this seed then starts to grow, and what is still quite unclear for us is how the shape anisotropy happens at this stage, how these spherical seeds, more or less with multiple facets, start to develop in specific directions. However, the next step is the surface growth, and then if you are able to control this growth by controlling the parameters, you can experimentally have a plethora of shapes, as I showed in the previous slide. But we were very much interested in understanding these 2 processes in further detail, to understand the reduction process and also how this growth is happening. So moving on further, we said that experiments would not be enough, so we started combining experiments with modeling and simulations. So we started taking help from molecular dynamics to understand how these micelles are influencing the growth process, and also looked at modeling, transport modeling, to understand how these spheres are forming these rods as a starting point. So I'm not going to show all the results, since I decided to focus more on what applications they have, but I'll at least show you one slide on how we try to combine experiments with simulation and modeling. So these are the 3 different shapes which we were formed at 3 different ratios of the surfactant and co-surfactant. So by using molecular dynamics, I hope we are able to show this, we built this gold seed, and then in this box started putting the gold atoms, so the AU0 atoms, and started to understand how these are being transported to the surface and how they are orienting along with the surfactants. And this is something that is one part of the study, and the other part where we are looking at how these initial shapes, using transport equations, we are able to define, for example, this bow tie shape of the nanoparticles. The other thing that we learned is that in this field, we need to produce a high or a scalable process. So we have tried to look at scaling up our production in different ways. One option is by using millifluidic channels. So, and the other option, as I'll show you in the next example, is by using reactors, or taking from batch to semi-batch and to continuous processes. So we are trying to kind of mimic the batch reaction that I showed in the previous slides into a millifluidic setup, whereby we'll pump in the growth solution, the seed solution, and then it's a carrier fluid. And the carrier fluid is primarily in order to have this two-phase flow, so that in each droplet we can have much more controlled reaction, and there will be no fouling of these millifluidic channels. And then the idea here is to pass them through this millifluidic channels after the droplet is generated, and each droplet is then our microreactor where the reaction will happen. And then after the particles are synthesized, we will separate them using this porous capillary separator so that we are able to then cycle back the carrier fluid. So to have the concepts of not using too much of the carrier fluid as well. And where the study currently is, we are also trying to set in an online or inline spectrometer so that the spectrometer can be tuned based on what wavelength we get for these specific gold nanoparticles, and then it can control the flow rates here so that we are able to change the LSPR or this the wavelength where we have the maximum absorbance. That can be shifted, so we can basically create different shapes by doing proper control. So this is how the setup looks like. This is the coil setup. It is put in a water bath to have it at the temperature of 35 degrees. And then we also have the separator, which is plugged in here. And then the green one is where we get the solution, our reaction product, and the red one is a carrier fluid. So it does perfect separation by using de-wetting and wetting processes we have learned in the other section before. So from here we are already able to produce these rods, but at the time, using residence time of 10 minutes and 30 minutes of aging time, we see that we have quite a good control, but now we are working to fix or reduce this aging time as we speak. So then why or how do we want to use these gold nanoparticles? And one application where we have been trying to tailor these particles for is within biosensing or within sensing of specific oligonucleotides. So for that I'm going to take help of these spherical gold nanoparticles, which by themselves, as has been shown before, has a very nice absorbance versus wavelength. So this is a UV-vis spectra. This is the LSPR, and that's around 520 nanometer. So what we did is that we took these gold nanoparticles and then functionalized these gold nanoparticles with an oligonucleotide or antisense oligonucleotide or ASO. And after the functionalization process, you can see that there is a development of two peaks, and the longer peak is also representing that we have successfully bound this antisense oligonucleotide, and these were for the coronavirus. And once this antisense oligonucleotides were functionalized onto the gold nanoparticles, we use them for RNA samples from patients. And as you can see on this plot, this is an optical parameter that I won't be able to disclose due to the confidentiality of the work. But we are able to see a very nice trend as an increase of the concentration, not completely linear, but in a certain range of concentrations, they are also quite linear. So currently we are looking at method development for licensing this particular technology. We went one further to continue this work, and now there is an ongoing project called the NanoSyn Sense with IIT Madras and us in NTNU, where we are trying to understand the growth mechanisms using transport models and equilibrium thermodynamics. We are doing microfluidic synthesis or millifluidic synthesis, and then at IIT they are going to fabricate biosensors, and this is more towards detection of LPS in bacteria. So moving on to the next story that I wanted to share, which is also quite recent, and I guess no one needs an introduction to the novel coronavirus. We have been using iron oxide nanoparticles that were synthesized by co-precipitation. So it's a process where you add a salt mixture, +2 +3 ions, very traditionally done in a base like ammonium hydroxide. And this leads to the formation of this tiny, around, let's say, 10 to 12 nanometer magnetite iron oxide nanoparticles. And then in the second step, we coat them in a very traditional Stover's method. So we grow a silica shell around these iron oxide nanoparticles. And by this picture, you can see that these particles are extremely magnetic. And we have, over the time, we have tried to look into a lot of these factors by which we can control the size and shape. And as I mentioned at the beginning, our main interest is to understand how these different parameters control the size and size distribution of these particles. So just to show you, in this particular study, we also focused a lot on the morphology of the particles. So we saw that we are able to tune the morphologies from these irregular structures to fused structures, and perfectly spherical is what we would actually want for having high sensitivity and good control of our test methods. For the purpose of time, I will not go through the details on this particular slide, but I will rather show you a bit of a mapping that we did with the two solvents, what kind of shapes we get, and more importantly, as I said, we want to use their magnetic properties. So, however, although the spherical properties are much more monodisperse than what we would like them to be, their magnetization is quite low compared to the irregular structures. And when you talk to people in the clinics, I think they are not so interested in your particles being extremely spherical or monodisperse. They would rather like to have a quicker test because everything runs on a shorter timeline. And some of this work actually was catalyzed during the pandemic. So I thought that it would be very interesting to kind of quickly say at least a couple of slides on how we worked on a known technology. We have been working in the lab for a few years, and at that time I was a postdoc in the same department. So we had received a request from the hospital that we are running shortage of kits, and Norway went into lockdown on 12th of March, so it's almost within a week that there was shortage of kits. And as you might know, it's a very small country with 5 million people and not at all prioritized when it comes to getting supply of kits. So we wanted to be robust and develop something which can happen within Norway. So there were some tests carried out in the Department of Clinical and Molecular Medicine. 23rd of March, we were contacted and we were using these beads for water treatment. And this was also something I talked about a few years back in one of the workshops here at Jadavpur University. And the similar beads, we started testing them out. And over the weekend, we had the test. This was a Saturday, Sunday, quite similar to a Saturday, Sunday now. And the beads started to work. So 1st of April, we established contact with the health authorities of Norway that there is a method we have developed within the university, collaboration, interdisciplinary collaboration between two departments which had never, or two groups which had never collaborated before. 3rd April, we filed 2 patents, and then on 17th April, this method was approved by the health authority for use of testing in all over Norway. And this whole process, what I wanted to emphasize, took less than 1 month to take it from the lab scale into a test method that was helping ease the burden of the pandemic in the Norwegian society. And on 17th of May, we signed the agreement with the Norwegian authority to deliver 5.1 million test kits for testing the whole population. And this is a brief cartoon. It's a very traditional PCR-based test, whereby you use a lysis buffer that opens up the virus, and then we add in our magnetic nanoparticles. So the magnetic nanoparticles are not specific to coronavirus, and these can then bind to the RNA, and then you use a magnet to separate out the RNA, do an elution step, and then you do RT-PCR to understand if it is coronavirus or another virus. And this happened in the Department of Chemical Engineering at NTNU. We produced close to 20 million of these test kits over the period that followed, and it was a huge team. And of course, a university is not set to produce. So in 2021, we established a startup company called Life Scientific, where I'm currently serving in a role of the CTO for the company, which is mostly producing these and other kind of nanoparticles for life science and diagnostic purposes. And we successfully provided these kits to Denmark, close to 1 million, to Brazil, and also in India, the same test kits were used in 2020. But as a part of the Corona project, or the NTNU Corona test method, we continued the work and we established a particle engineering center at our department, which is, I'm also the center manager for this, with the aim of using chemical engineering to understand particles and also set up more relations with industries in the same field using a sustainable approach. So the whole center is built on a sustainability framework when it comes to hiring, when it comes to lab usage, consumables, and also targets, etc. So I'm not going to talk too much about the center, but I'll show one application. So right now we have 3 main areas. One area where I'm presenting today is nanomedicine, but we are very much working with industrial partners within hydrometallurgy and recirculation of batteries. So basically, as I give the example, in one case we make solid particles from solution, in the other case we dissolve the solid particles back into the solution. So we are kind of closing the loop, but we also work in environmental applications within water management and partly in CO2 capture. But the strength of the work is within particle design and particle characterization. That's where we are mostly working in all of these applications, and the applications are done in collaboration with different departments and universities. And let me show you for the last 2 or 3 minutes one final application in diagnostics, as I said, which is in DNA size exclusion. So as I showed you, the corona beads that we made, they can extract all the nucleic acids. But in any application downstream, you would like to separate these nucleic acids. You would like to chop off or take out the DNA, you would like to take out the RNA, and then once you have taken out the DNA, you would like to distribute the DNA based on sizes. Okay, so you would like the shorter chains to be segregated from the longer fragments of DNA. So that is what is referred to as DNA size exclusion. So you basically want to ladder the different DNA fragments based on their sizes. And this we do with polymer-coated iron oxide nanoparticles. So again, we use traditional polymerization process. The monomer is acrylic acid. We use iron oxide nanoparticles, which I've showed you before for the corona test. And then we do a polymerization reaction using free radical polymerization. And then we end up with particles which have carboxylic groups. And mind you, the carboxylic groups are very, very important for making this DNA size exclusion efficient. And we, again, optimize a lot of these input parameters and look at how these affect the size and the density and also the magnetic properties. And for the purpose of time, I've not included all those results, but I would rather show you what it means in an application setting. So this is the ladder I was referring to. So these are the different sizes of the DNA, and this is how you would actually, the different cuts are marked here. So this is a typical ladder. So when we use the bare iron oxide nanoparticles, you can see that all of these end up in the higher fragments. So everything is basically collected. So it's the non-specific binding of the DNA fragments. Whereas when we start to use our optimized recipes for these polymer-coated iron oxide nanoparticles, you start to see that the different cutoffs are being formed at different ratios of the particles. That means if you are having 0.6 times, you would be able to get the higher fragments, whereas if you use 2 times the particles, then you will get almost all the fragments. So this is just to ease. And then when we look at different particle compositions, you get also different fragmentation capabilities. And let's compare this to the state-of-the-art, the Ampere, which is the bead currently used in this field. We are quite close with this particular sample, and more optimization is required. But this is also something that works into a new product, for example. So I think with that, I would like to conclude what I wanted to present today. I have shown you probably how we can control the particle properties by controlling the formation mechanisms, understanding how these reaction conditions help engineer particles with the properties we want. And as I said, our main focus is within surface functionalization. And finally, we do a lot of this iterative optimization of the surface chemistry. So we go back and forth. The beauty of how we now have structured the research is that when we see that some of these research is quite close to becoming a product, we have a very good mechanism for licensing that technology into the startup. So it's a very good way of doing basic research and applied research together, and utilizing the knowledge that we develop over time to products that can actually help sustainable healthcare. So with that, I think I would also like to thank my research team at NTNU, many of whom have contributed to today's presentation, and thank you to all for being so patient and staying back so late in the evening. Thank you.
Thank you, Dr. Bandyopadhyay, for your informative lecture on nanoscience and its application. It was really such a lucid and informative talk. Thank you. I would request the audience if there is any question, please.
Can you please go back to the slide of antiparallel nanoparticle? Which one? The antiparallel silver, gold or silver nanoparticle, something was there. No? This one? Yes. With the help of CTA. Yeah. So, yeah, CTA is acting as a capping agent for nanoparticle preparation.
So the role of CTAB here, as we understand, is that it is, well, that is also something we are still trying to understand, but at the starting point, I would say that it is a growth directing agent, so it specifically binds to certain facets of the gold. So gold has these FCC structure, and then you have 100, 111, and 110. So it protects some of these planes, and it allows the other planes to grow. So that's the main role of CTAB. So without CTAB, we won't be able to have shape anisotropy. CTAB is very important.
So not for the purpose of sensing.
Not for the purpose of sensing. So when we will, so I didn't mention that, but when you have these rods, instead of a single spectra, a single peak, you will get at least 2 peaks. And the peak which is towards a higher wavelength can also be used later on for converting light to heat, for example. So these would be then used for photothermal applications than for sensing.
I would like to conclude the session with the felicitation round, requesting Professor Ranjana Chaudhary ma'am to kindly felicitate Dr. Das and Dr. Bondurwat. We are really running late, but thank you for your patience sitting here and attending the lectures. There's a cultural session next. Anybody interested may please proceed to that. Thank you. I'm ending here.
Good.